Welcome to Alpha Online Education YouTube channel. So in that we are going to discuss about intermediate second year. The 15th unit will be semiconductor electronics, materials, devices and simple circuits. First of all, the matter can be classified into three types. Those are solids, liquids and gaseous state. Can be stated three types. In that solids, liquids and gaseous, the free electrons can be easily moved through the solids, not from the all solids. So according to that solids, their conductivity of electrons or resistivity, according to the conductivity and resistivity, that solids can be classified into three types. Those are metals, that means to say conductors and insulators and semiconductors. First of all, the solids can be classified into three types on the basis of they can be the electrical conductivity or resistivity. Electrical conductivity or resistivity, on the basis of that conductivity and resistivity, solids can be classified into three types. Those are conductors, insulators, semiconductors. In that case, first of all, the conductors also called as metals, and the second one insulators, and the third one is semiconductors. Here in the solids which are having the high conductivity or low resistivity, that means to say due to they have more free electrons, large free electrons consisted, so that's why they are called as metals. Means if in case of correct if we see the electrical lines, so some of the metals having the more large free electrons, so that's why they can conduct the electrons more and more, so that's why they are used as for the electrical purpose. And in household also we can use the copper wire. In the list we can see that whenever that remove the core, whenever remove the top of the layer, then we can see the copper leads, which is having that more leads can be transfer the more conductivity of electrons. So that's why the metals means which is having the large number of free electrons, which can be high conductivity and low resistivity metals are called, solids are called metals or conductors. Metals or conductors, due to they have more large free electrons, is there, so that's why we can say that they are the metals or conductors. Conductivity of metals between the 10 to the power of 2 to 10 to the power of 8 Siemens per meter. Siemens per meter means here Siemens is the unit for the conductivity, that means to say the reciprocal of resistivity. The reciprocal of resistivity means in ohm universe. Ohm universe will be the Siemens. So we can say that Siemens be the unit for the conductivity, we can write that. Then the resistivity will be 10 to the power of minus 2 to 10 to the power of minus 8 ohm meter. Ohm meter means here the large conduction will be possible due to the conductor, so that's why they have possess high conductivity and low resistivity, and they have large free electrons. So that's why their conductivity will be between the 10 to the power of 2 to 10 to the power of 8 Siemens per meter. That will be the between the light solids, they maintain the conductivity between these values, and at the same time here the resistivity will be 10 to the power of minus 2 to 10 to the power of minus 8 ohm meter. So the examples are aluminium, copper and iron and silver. Silver is the best metal conductor that can be conduct more and more electrons without any resistance. Conductors, silver will be the more conductor. The next one is according to the conductivity and resistivity of the material solids. Another thing is insulators. Solids can be classified into the insulator. Insulators means they have high resistivity and low conductivity nature solids are called insulators, means they can't exchange, they can't allow to pass the electrons through the materials. Those are called also insulators. The materials which cannot allow the flow of electrons, which resist the flow of electrons, are called insulators. That means to say they cannot conduct the electrons, means like wood, rubber, like that. Whenever if the poles, concrete poles are to build the electric lines, will build with the poles, with the concrete poles. Those are also the insulators. That means here the conductivity solids which possess very low conductivity and high resistivity, means they do not allow the flow of electrons through that materials are called as insulators, like wood, rubber, clay and putty, like that. Here the conductivity of that insulators will be 10 to the power of minus 11 to 10 to the power of minus 19 Siemen per meter. Means here that will be the resistivity, means the conduction will be between 10 to the power of minus 11 to 10 to the power of minus 19 will be lies, and resistivity will be the reciprocal of, so that's why 10 to the power of 11 to 10 to the power of 19 will be the resistivity, means having the more resistance, means they do not allow the flow of electrons, which is having the due to that less flow of electrons, no free electrons. The conductors, the material solids do not have any free electrons, so that's why they cannot conduct the electrons. Next, the rubber, glass, plastic, putty, those are the examples for the insulators. The next one is semiconductors. In that word also is there semiconductors. Semi means there is no total conduction and there is no any total restriction, means they allow the partial allow of electrons through the materials are called semiconductor materials, which is having the conductivity or resistivity between the conductors and insulators. The conductivity and resistivity nature will be between the insulators and conductors. So that's why they cannot allow the electrons through the materials which are having the partial conduction is there. That are the semiconductor materials. Those due to that these have very few free electrons are there. So that's why here they cannot pass all the electrons through the materials and they cannot restrict the total electrons. So that's why they can be partially allows the flow of electrons. So those are called as semiconductor materials. Their conductivity will be 10 to the power of minus 5 to 10 to the power of 6 and resistivity will be 10 to the power of 5 to 10 to the power of 6 ohm meter. And the examples are germanium, silicon, carbon, etc. These are the examples for the semiconductor materials. Like fifth group elements are will be the using as a fifth group elements, and as the germanium, silicon, carbon, these type of materials can be used as a semiconductor materials. Nowadays we are using widely, semiconductors are using widely, and also the solids can be classified into the two types also, crystalline solids and amorphous solids. Here crystalline solids having the definite shape, and each and every part, whenever we broke the crystalline solids, then each and every part having the definite shape is there, and each and every shape having the same strong as the total body is there. So and according to the amorphous having does not have this definite shape. If in case of a glass is there, if we broke the glass will breaks into the different types of. That's why the amorphous and crystalline solids also that can be classified by the nature of the solids. According to the band theory of solids, band theory means here we know that electrons are revolving in an atom in a around the nucleus like this. If in case of this considered as nucleus, then electrons are revolving around the nucleus. In the outermost orbit electrons which are revolving in the outermost orbital having that valency electrons, means the outermost orbital. In the outermost orbital the electrons which are revolving around the nucleus having the high energy, even though the band orbit is filled, partially filled, they having the more energy levels. Their bond with the nucleus will be less. The electrons which are staying revolving in the outermost orbital, that is called as a valency orbital. that electrons are called as valency or electrons. So that in the case of the energies, the range of energies of these electrons, valency electrons of the particular orbit, means in the orbit energy can be considered that whenever the electrons are revolving in that is the band energy of an electron. We can say that band energy of an electron. So that's why whenever the electrons are revolving in a particular orbit in atoms of a solid, the range energy is possessed by that electrons. The energy possessed by that electrons is considered as a energy band. The band which is contained by that is called as a energy band. According to the what is meant by the band, means the energy possessed by that electrons, either the few electrons or few electrons. If there is no any electrons in the band, then that will be the insulators. Like this here, so we can say that the what is valency band, means energy bands of according to that the some important bands in the solids. Those are valency band and conduction band and forbidden energy gap. These are the most important thing to learn for the further concepts. First of all, what is valency band? Valency band means the range of energies, either the band which is having by the electron, the range of energies or that is band possessed by valence electrons. The valency electrons which is in the outermost orbital possessed by the some high energy level, those are electrons are called valency electron possessed by the energy range of energies are called the valency band. Valency band, that is here the second highest band is called as a valency band. This is the and conduction band means it is having the free electrons. If in case of this having the free electrons, then only there can be large circulation will be possible through the valency band to the conduction band, then only the conduction will be possible in conductors. Either in case of there is no free electrons in conduction band, means conduction band, if the conduction band is empty, then there is no conduction between the two bands, so that can be considered as insulators. If in case of conduction band having the partial electrons, few electrons, then there is some of the less transfer of electrons from the two bands, the forbidden gap will be less. Then only that is the partially conduction will be possible through this, so that's why called as semiconductors, the energy levels. In the case of energy levels are having the 3 electron volts of energy levels. If in case of the forbidden gap having the 3 electron volts, means energy gap which is equal to 3 electron volts, then there is no conduction between the conduction band and valence band, then electrons can get into the from valence band to the conduction band. Valency band means the energy bands which is the having the valency electrons which is ready to escape from the orbital, which is ready to jump from the one orbital to the another orbital. So those are called as the outermost orbital electrons possess some high energy level which is bonded to with the nucleus is very less energy will be possessed with the between the nucleus and the valency orbital electrons. So that's why the range of energy is possessed by the valency electrons, means the conduction band electrons in the which is having the by the conduction is called a conduction band. And the next one is forbidden energy gap. If in case of the forbidden energy gap means is nothing but the simple thing is the separation between the conduction and valency band and conduction band, the separation between the conduction and valency band is called as a forbidden energy gap. If in case of the forbidden energy gap is 0, means like this, if in case of if the forbidden gap energy Eg is equal to 0, then here the valency band and conduction band will be like conduction will be directly possible without any resistance. These are called as conductors. In the conductors, the forbidden gap will be 0. There is no separation between the both conduction and valency band. Next one is insulators. In insulators, we can say that then the distance between the separation between the valency band and conduction band will be Eg is equal to 3 electron volts, or 3 is more greater than 3 electron volts is equal to 3 electron volts. Then only there is no conduction band will be there is 0 conduction, 0 free electrons. 0 free electrons. Then only there is no conduction between, there is no electrons will be jumped from the valency band to the conduction band, then the conduction will be 0. So that's why it can be considered as insulators. The solids can be considered as insulators. If in case of the energy level is less than the 3 electron volts, means energy level is less than the 3 electron volts, then semiconductors, means the high energy electrons can jump from the valency band to the conduction band to fill the conduction band to conduct the to flow the electrons through this. So here it is that high energy orbitals can only travel from the conduction band to the valency band to the conduction band. This is about according to the band theory of solids, the conductors, insulators and semiconductors. Semiconductors can be classified into two types by their purity. So in case of a pure semiconductors, means without any semiconductor, the tetravalent semiconductor materials like germanium, silicon, carbon, like whenever they are bonded with another germanium particles in an atom, then the surrounded 4 electrons are bonded, make the covalent bond with the neighbor germanium atoms. Make the covalent bonds with the neighbor stable atoms, which is having that equal covalent bonds are bonded with the neighbored germanium atoms. And as in case of, if we take the silicon also, the total 4 electrons are bonded with the another surrounded neighbored germanium atoms in the molecule. Those are the pure state of semiconducting materials, the pure form of a semiconducting materials. The pure form of a semiconducting materials are called intrinsic semiconductors. What is that? Intrinsic semiconductors. The pure form of semiconducting materials are called intrinsic semiconductors. In that conductors, there is a pure germanium 4 electrons in a valency band. They make the covalent bond with the neighbors. They make a covalent bond with the neighbors. When make covalent bonds with the another germanium, whenever the atoms, when such a semiconductor is added, to this germanium, then some of the covalent bonds will break. Some covalent bonds will break due to this, the thermal hesitation. Whenever we apply some of the semiconductor, that due to the thermal hesitation between the molecules, electrons, then some of the electrons will break the covalent bond for the conduction. They are separated from that bonding. They separated from the bonding by giving some of the energy to the electron. Then they separated from the bonding and for the conduction. So that's why when the electron is separated, when the electron will separated from the bond and there is a deficiency of that place. Some of the deficiency of that place which acts as a region of positive charge. Region of positive charge means that is called a hole. The positive region will be happened whenever the electron gets drifted from the covalent bond, separated from the covalent bond, and some of the deficiency will be happen. That region is called as positive region, called a hole. So that in case of this is a pure form of a germanium is surrounded with the same germanium atoms, bonded with the covalent bonds are made with the neighbor germaniums. To conduct, if we added some semiconductors, then only some of the electrons separated from the covalent bond and there is a deficiency of electron in the bond. So the deficiency is called positive region. That is considered as a positive region, is called as a hole. This is about intrinsic semiconductors. It is nothing but the pure form of a semiconducting materials is called intrinsic semiconductors. The pure form tetravalent means tetra covalent bonds are made with the neighbor same materials. Then it is tightly bonded with that one, there is a constant material, then only when such semiconductor is added to that one, the electrons get drifted, means separated from the covalent bond, and for the conduction and some of the deficiency will be happen with the positive region, that is called as a hole. This is about intrinsic semiconductors. If we come for the another one, that is extrinsic semiconductors. This one is intrinsic semiconductors, that's a pure form of semiconductor. This is extrinsic semiconductors, means when trivalent or pentavalent, when the trivalent or pentavalent impurity is mixed to the pure semiconducting materials. When the pentavalent or trivalent impurities added to the pure semiconducting materials, then conduction will be increases of that materials. There is a conduction will be increases of material. If in case of just take a pure water is a insulator. Pure water is a insulator. They can't conduct the electricity. That pure water cannot conduct the electricity. If we added some of the salt, in the water, pure water, then means we are adding some impurity to the pure material. So like that, here extrinsic semiconductors means by adding the pentavalent or trivalent impurities added to the pure tetravalent components, means semiconductor materials. When pentavalent or trivalent impurities are added to a pure semiconductor materials, then conduction will be increases. The conductivity of that materials will increases. So here it is that the mixing of impurities to the pure semiconductor materials are called doping. When the mixing of impurities to the pure semiconducting materials, pure semiconductors, is called doping. By the doping we get the extrinsic semiconductors. The resulting semiconductors called, whenever we dope that, the trivalent and pentavalent impurities are added to the pure semiconductor materials like tetravalent components, then we can get the another type of extrinsic semiconductors are called extrinsic semiconductors. Then if we added the pentavalent, then we get the another type of semiconductors, and whenever we added the trivalent components, and another type of semiconductors will be formed in the extrinsic semiconductors. By the doping, by the mixing of the impurities, we can get the two type of semiconducting materials. Those are p-type semiconductors and n-type semiconductors. By adding the impurities to the pure semiconductor like a trivalent and pentavalent, by adding, then we can get the two type of semiconducting materials. Similarly, here we can say that the p-type of semiconductors and n-type of semiconductors. Let us see what is a p-type semiconductor and n-type semiconductor. By adding the impurities to the extrinsic semiconductor materials, means tetravalent semiconductors, by adding the impurities, then it can be formed another two type of semiconductors in extrinsic semiconductors. Those are p-type semiconductor materials and n-type of semiconductor materials. Already as we know that. So in p-type of semiconductor materials, when the impurities adding to the pure semiconductor materials, then that process is called as doping, already we studied about. And when the trivalent compounds, trivalent impurities, the trivalent impurities are added to the, doped to the tetravalent semiconductors or intrinsic semiconductors, is called P, then the p-type of semiconductors are formed. Means by doping or adding the trivalent impurities to the pure semiconducting materials or intrinsic semiconductors, then the p type of semiconductors are formed, like aluminum, gallium, indium and boron. Those are the trivalent impurities. When the trivalent impurities, it consists of 3 electrons in the valency band. So here is that, here is the 1 electron and another one is these 3 electrons are make bond with the another neighboring germanium material, means germanium is the tetravalent and boron is the trivalent. So it is consist of 3 electrons and germanium consists of 4 electrons. These 3 electrons are made the covalent bond with the neighboring germanium materials, neighboring germanium semiconductor materials, and another side of there is insufficient of means incomplete bond is there, which is in this region already we studied some of the deficiency of an electron in a region, that is a positive region. That is a positive region is considered as a hole. This is a hole. Hole is happened. The insufficient electron is there to make the bond with the neighboring germanium material in with the one boron atom. So here it is that if in case of the number of atoms is constant a atom and the number of borons are added in the molecule, so that's why here another boron is also there is a deficiency also there, and another, if the boron is added, another deficiency also there. So here is the main carriers, main conducting due to the by accepting the impurities, these holes will be play the key role by in the conduction. Majority roles plays by these holes. So that's why we can say that when the energy band, here the valency band consists of holes and this is the conduction band. In this conduction band there is a forbidden gap is there, this is the Fermi level, and the holes can accept the electrons to this level. So that's why whenever the impurity is added to this one, then the Fermi level will move towards the valency band. Whenever this will move to the valency band, the electrons will jump into the valency band and they will conduct. They will connect by accepting the electrons, means the impurities which is adding to the pure semiconductor materials, the impurities are acceptors. Always the impurities are acceptors in a p type of semiconductors, means which is ready to accept the impurity because of due to the lack of an electron is there. So that's why it is adding, it is accepting, it is ready to accept, ready to take the another electron. So that's why hole is there, the insufficient place is there to fill this place. It always accept the another impurities. So that's why here the boron is called as a acceptor. Boron is called as a acceptor. So in case of this, due to this one, by adding the impurities, the more holes can be played the key role in conduction. So that's why here the number of holes in valency band, the number of holes in valency band is more than the number of electrons, in the conduction band. Means the electrons will be less in the conduction band, in the valency band the electrons are more. So insufficient place is also there in the valency band, it is ready to accept in always. So that's why the Fermi level moves towards the valency band. So here it is that the number of holes present in a valency band, means here in the holes will be found with this is a stable bond, this is also stable bond, this is also stable bond, but this is unstable bond which is ready to accept, insufficient storage is there. So that's why here the which is ready to accept an electron. So that's why here the valency band consists of more holes than the electrons. Here more holes than the electrons. So that's why here we can say that the number of holes in valency band are more than the number of electrons present in a conduction band. So that's why here the more holes are the majority charge carriers, means due to the holes the conduction will be possible with the p type of semiconducting materials. So that's why here the holes are the majority charge carriers, due to the holes conduction will be possible, and due to the electrons, means electrons are less in conduction band. So that's why here the minority charge carriers can be considered as electrons are considered as minority charge carriers. Holes are the majority charge carriers, and electrons are minority charge carriers. Holes are also called as positive charge carriers. Majority charge carriers are holes. These are the positive charge carriers, which consist of a positive charge, and Fermi, so that's the Fermi level shifts towards the valency band. So here it is that there is no charge on p type of semiconductor because of the p type of semiconductor materials are formed due to the combination of a neutral atom. So that's why the p-type of semiconducting materials are neutral. The p-type of semiconducting materials are neutral. Once again, p-type of semiconductor means by doping with the trivalent impurities to the tetravalent semiconductors or intrinsic semiconductors are called pure semiconductors are called here the p type of semiconductors. Here the borons are the acceptors because of due to the boron the lack of electron will be happen because of insufficient covalent bond is there, inefficient. So that's why this the lack of electron is there, hole will be formed, positive region will be formed. So that's why here the holes will be more in the valency band and in the electrons are less in the conduction band. So that's why the Fermi level shift towards the valency band. So here it is that here the boron is the impurity, so that's why in p type of a semiconductor borons are the called as a acceptor, means that is always ready to accept impurities, means accept the electron. So that's why here the more charge carriers are majority charge carriers are hold and minority charge carriers are electrons, because of in this p type of semiconductor due to the holes the conduction will be possible more. So that's why here holes are the majority charge carriers, and as well as the number of holes present in the valency band is more than the number of electrons present in the conduction band, and as well as the p type of semiconductors are combination of the neutral atoms, so these are called as neutral. The semiconducting materials, p type of semiconducting materials are neutral. Next one is n type of semiconducting. N type of semiconducting materials are N type of semiconductor. Earlier we discussed about P type of semiconductor by adding the trivalent impurities to the material. Then the pure intrinsic semiconductor, whenever the trivalent impurities are added to the tetravalent semiconductors, then P type of semiconductors will be formed. In case of by doping or adding or mixing the pentavalent impurities to the pure semiconductors or tetravalent semiconductors or intrinsic semiconductors, by doping or mixing adding the pentavalent impurities which is having the 5 electrons in the valency band. So here it is that when by doping or adding the pentavalent impurity to the pure tetravalent semiconductor or intrinsic semiconductors, the N type of semiconductors are formed. The N type of semiconductors are formed. Here the pentavalent impurities are arsenic, stibine means antimony, and phosphorus. This type of materials are pentavalent materials which is added to the pure germanium or silicon, which is having the trivalent, means 4 electrons in the valency orbital. Here the phosphorus is having the 5 electrons in the valency orbital, so that's why whenever the phosphorus impurity added to the germanium, pure germanium, then the 4 electrons are made the bond with the covalent bond with the neighboring germanium molecule electrons, which is having the tetravalent, 4 electrons is there, 4 electrons is there. Phosphorus also with its 4 electrons make the bond with the neighboring germanium, and one excess electron, because it is having the 5 electrons in valence orbital, so that's why one excess electron will remains to create the bond, means for the conduction. This will be the one of the free electron which is ready to make the bond with the another one. So here this is the donor. The impurity which is added in the N type of semiconductor material, the impurity added here are the donors, which is having the excess electron, excess free electron. These are the bonds, created the bonds. But the excess electron which is ready to add donor, which is ready to give the electron to the another inefficient bonds. So here it is that the conduction band is having the more electrons if we compare with the number of holes. So that's why here this is the donor level. Because of excess of electron will move towards the conduction band, it is easily conduction, it will easily jumps into the valence band and as well as acquire the holes, and here the conduction will be possible due to the electrons, excess electrons. So that's why here in the N type of semiconductor materials the impurities are the act donors. These are the phosphorus is the donor. Phosphorus is a donor. Donor means which is ready to give an electron to the another one. So here excess electrons will be there. Whenever these are another bond with the, there is an excess electron will be happen whenever these bonds are created, and here is also wherever another bonds also created, then here also another phosphorus will be having the more excess electron. Like this, the excess electrons are the play the key roles in N type of semiconductor to conduct the electricity, means electron. Wherever the electrons are moving from this, then number of electrons in the conduction band is more than the number of holes in the valency band. So here the Fermi level will move towards the conduction band and another one the conduction will be possible, conduction will be happen. So that's why here due to the excess electrons conduction will be done. So that's why here the majority charge carriers are electrons and minority charge carriers are holes. So that's one Fermi level shifts towards the conduction band. Here there is no any connection will be possible, means there is no charge on the N type of semiconductors, because of N type of semiconductor materials are formed by the neutral atom, So here it is that there is no charge, these are called as neutrals in nature. We can call it as a N type of semiconductors are neutrals in nature. This is about N type of and P type of semiconductor, intrinsic and extrinsic semiconductor materials. Next we will know about the what are the uses and what is the formations whenever the combined the P type of and N type of semiconductor materials are added, then what will the type of actions will be possible, what are the applications by the P type of and N type of the semiconductors, insulators and conductors, and types of semiconductors, that means intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors means the pure form of a semiconductors are called intrinsic semiconductors. By doping or adding some impurities to the pure semiconductors, we can get the extrinsic semiconductors we can get. Then what is the difference between what is the comparisons between the extrinsic and intrinsic semiconductors? Let us see. Here the distinction between the intrinsic and extrinsic semiconductors means what is the comparisons and what is the differences between the intrinsic and extrinsic semiconductor. This is first of all intrinsic semiconductor. Intrinsic semiconductors. We know that what is intrinsic semiconductors? It is a pure form of a semiconducting materials with no impurity atoms are added to that, and it's an example for that the crystalline form of a germanium and silicon, means there is no any impurities in that matter, like pure water. That is also that does not contain any impurities in that. So here that it is a pure semiconducting material and no impurities are added to it. So example are the silicon and germanium are the examples for the intrinsic semiconductor. The next one is the number of free electrons in conduction band and the number of holes in a valency band is exactly equal. Both are in the conduction and valency band. We know that whenever if we take the diagram, then this will be the conduction band and this is the valency band. The number of electrons contained by the conduction band and number of holes in the valency band both are the same. Equal number of holes are conduction by the valency band, which is equal to equal number of electrons contained by the holes in valency band, and exactly equal to the very small indeed. So that's exactly equal and very small indeed. So that's why here we can say that in valency band and at the same time conduction band, in the conduction band electrons and valency band holes are the same in intrinsic semiconductors. And also due to that the same amount of electrons and holes there is a small conduction, electrical conductivity is very low. Electrical conductivity is very low, and whenever the electrical conductivity is low, it is a function of temperature alone. It is a function of temperature alone. If we give the temperature to that one, then some of the electrons will exist at a high temperature. They will move into the high energy levels. So this is about intrinsic semiconductors. If we compare with the extrinsic semiconductor with the intrinsic semiconductor, let's see. Here we said that the pure semiconducting material, intrinsic semiconductor is a pure semiconducting material, but in case of extrinsic semiconductors, here it is a prepared by doping, means by adding the impurities to the pure semiconducting materials, means like intrinsic semiconductors, means we are adding some impurities to the pure form. So that's why here it is prepared by the doping a small quantity of impurity atoms to pure semiconducting materials. For example, the silicon germanium crystals are doped with the fifth group of elements like impurity of atoms like arsenic, antimony, phosphorus, indium, boron, aluminum, like that elements which is added to the pure germanium and silicon atoms. Then we can find out the extrinsic semiconductors. By adding the impurities also, if the types of impurities added, we can get the another types of semiconductors, that is p type of a semiconductor and n type of a semiconductor also. By adding the impurities, then if in case of pentavalent impurities are added to the pure form of a silicon and germanium, we can get the n type of a semiconductor. And trivalent means third group elements which is added to the pure form of a silicon and germanium. Third group of impurities added to the pure form of silicon and germanium, then we can get the p type of a semiconductors, like that. Here is also these are all arsenic, antimony, phosphorus, indium, boron, aluminum. These are the impurities which is added to the silicon and germanium atoms. So then we can get the extrinsic semiconductors. So that's why it is prepared by the doping, by adding the impurities to the pure form of a semiconducting material. So the number of free electrons and holes are not equal in the extrinsic semiconductors because of we are adding the impurities. So that here is that the number of free electrons and holes is never be equal. There is excess of electrons in n type and excess of holes in p type. So earlier we discussed about the p type of a semiconductor and n type of semiconductor, the majority and minority charge gate. Then after this one we will discuss about the what is the difference between the n type and p type also. So here is that whenever we added the impurities, then we can get the excess of electrons or excess of holes in the p type or n type of, means here the excess of electrons in n type and excess of holes in a p type of a semiconducting material. So the why then we applied the impurities, means added the impurities to the pure form of a semiconductor, then electrical conductivity is high. Electrical conductivity is high. So here the electrical conductivity is high. So that's why here electrical conductivity depends upon the quantity of impurities added to the atoms. Impurity added to the pure forms. Means if we add the more impurities, then conduction will be more, and it's a temperature dope, means here it is also depends on the temperature as well as it depends on the temperature and as well as whenever the quantity of atoms, quantity of impurities added to the pure form of a semiconducting materials. So here is the comparison. It's a pure form, it is a doped with the pure form doped with the impurities, and these are the free electrons and holes are same. Here free electrons and holes are not equal in extrinsic semiconductor. In conductivity is low in intrinsic semiconductors and conductivity is electrical conductivity is high in extrinsic semiconductors. So it is a function of a temperature, and it is depends on the temperature and as well as here the depends on the quantity of impurity atoms added to the extrinsic semiconductor. This is about the distinction between the intrinsic and extrinsic semiconductors. This is also one of the important question for the IPE public examination for 4 marks. So this is about intrinsic and extrinsic semiconductors. After knowing the distinction between the extrinsic and intrinsic semiconductors, now we are going to discuss about by doping the pure impurities we can get the extrinsic semiconductors. By doping the pentavalent impurities we can get the N type of a semiconductors. And if we added the third group is nothing but trivalent compounds to the, then we can get the P type of a semiconductor. Then what is the comparisons or what is the difference between the P type and N type of semiconductor? In this case of this small comparison is there, N type and P type of semiconductors are both are type of a extrinsic semiconductors. It is also P N type is also extrinsic semiconductor, and as well as it is also an extrinsic semiconductor like this. Both are the extrinsic semiconductors because of by adding the impurities or doping the intrinsic semiconductors we can get the doping the intrinsic semiconductors we can get the values, means I can get the P type and N type of semiconductors like extrinsic semiconductors. So that the pentavalent or trivalent, whatever the impurities are added to the pure form, then only we can get the different type of semiconductors in extrinsic semiconductors. In that, what is the comparison between the both of them? So here it is that N type of a semiconductor, which is an extrinsic semiconductor, by adding the pentavalent or fifth group elements, by adding the impurity of fifth group elements, or these are also called as a pentavalent impurities added to the pure germanium and silicon. Pure germanium and silicon means here we are adding the pure germanium silicon materials to, we are adding impurities to this one. So that is a pentavalent impurities. Pentavalent impurities like here whenever the impurities are added, then they provide the extra electrons in structure. Because of it is having that whenever we take the germanium and silicon, these are having the 4 electrons in the valency band. So valency orbital. So in the case of pentavalent, there is also 5 electrons in the valency orbital. So 4 make the covalent bond in the germanium electron, and the fifth group element electron will form the covalent bond. And there remains 1 electron without any bonding, which is having already, which is ready to bond with the another electron. So here the excess electrons can be produced in the structure in N type of a semiconductor material. So that's why the impurities of atoms added provide extra electrons in the structure. The extra electrons in the structure, already we did that. So whenever here if we take this, the phosphorus, which is having the 4 and excess electron 1 of the 5. Here germanium having the 4. This is the neighbor 4. Germanium is having the total. Whenever the germanium or silicon shared their electrons to bond covalent to make a covalent bond, and another remains 1 electron, the excess electron in the structure, it can be provide extra electrons in the structure are called these ready to donate the electron to another atom. The phosphorus, which is excess free electron is there, which is ready to donate to give the another bond to, it is ready to donate the electron. So that's why it is called as a donor atoms. Donor atoms in N type of a semiconductor, which is the impurities added to that one, they are called as a donor atoms. So here it is the donors. Then so that's why here the excess electrons can be conduction due to the, it is ready to give an electron, donate the electron. So that's why it gives the energy, it gives the electrical energy to the another one. So that's why the conductivity is possible due to the electrons, because of excess electrons is there in the N type of a semiconductor. So that's why here the majority charge carriers are electrons. The majority charge carriers are electrons, and holes will be less in the valency band. So that's why we can say that holes are minority charge carriers. Holes is there, but there is a electrons are more than the holes. So the density of electrons is more. Density of electrons in more in N type of a semiconductor if we compare with the density of electrons. So that's why the majority charge carriers are electrons and minority charge carriers are holes in the N type of a semiconductor. So here is the electron density, means the electron density is more greater than the holes density, because of number of electrons is more. So that's why the density of electrons is also more. Then the donor energy level is close to the conduction band, because of when here this is the conduction band and this is the valency band, it contains the more electrons in conduction band, holes will be less. The donor energy level which is close to the conduction band, because of more electrons are there, so that's why the conduction band will be more close to this place. So here that far away from the valency band, this is far away, forbidden gap is more between the valency band and the conduction donor level. And the Fermi level lies between the conduction band, donor energy level, conduction band and donor energy level, means between the Fermi level. Fermi level means, what is meant by the Fermi level? Every time we used to use that word Fermi level. What is Fermi level? So here it is that Fermi level is the highest energy state of that electron can acquire, obtained, the electron obtained, the higher energy state of an electron that can be obtained. As that whenever the temperature is increased, then there is electron also exist in the band. So that's why here that the Fermi level means the highest energy state level here that electron can acquire. So the Fermi level lies between the conduction band and the donor level. So that can be conduction is possible. So here is the donor energy level is close to the conduction band, because of which is having the more electrons are there. So that's why the conduction band, the donor level will be near to the conduction band, and Fermi level which is lies between the donor energy level to the conduction band, between the donor energy level to the conduction band. So that's why here the donor energy level and conduction band. This is about N type of a semiconductor. If we compare the P type of a semiconductor with the N type of a semiconductor, just what is the comparison? As is this is also extrinsic semiconductor, as well as this P type of a semiconductor is also extrinsic semiconductor. Because of we doped with pentavalent, we get the N type of a semiconductor. If in case of we doped with the trivalent or third group elements which are in periodic table, third group elements are third group in periodic table, then the obtained by doping third group elements impurities to the pure germanium and silicon. The pure germanium and silicon is doped with the trivalent compound elements or the third group elements. Third group, by doping the third group elements are it is also called as trivalent, right? So whenever the impurities are added, there is a lack of electron to make the bond with the neighbor germanium atoms. Means here already we did that one. Here germanium is there is a 4 electrons is there. Consider boron which is having the 3. So germanium is there, germanium make the, here is also germanium make the bond with the boron, and one of the lake there is no any electron which is ready to accept, which is ready to make the bond. If there is an electron, the germanium which is ready to accept, means to make the bond to be stable. The boron require one electron, there is a vacancy for electron. There is a vacancy for electron, that is called as holes. So here it is that the impurities added create vacancies of electrons, that is holes. In the structure we got the sum of vacancy for the electron to occupy the electron which is ready to accept an electron. There is a hole, that is called as hole. So here it is that the impurities added create vacancies of electrons, that is holes. There are the holes in the structure and called as acceptor atoms. These are the acceptor atoms which is ready to accept another electron from another atom, which is a 3 valency electrons are there. There is a lack of one electron to make the bond with the neighbor germanium atom. So it is ready to accept an electron from the other atom. So it is also called, they are called as acceptor atoms in P type of a semiconductors. So here the holes will be more whenever we take the number of electrons. If we compare with the neighbor, there is also boron whenever we make the bonds with the neighbors, the number of holes can be shown. So that's why here due to the holes which is ready to accept the holes, ready to accept the electrons by the holes, so that's why more holes will be formed in the structure, so that's why excess holes will be in the structure. So due to the holes, the conduction is going on in the p type of a semiconductor. So that's why here the conduction due to the holes, that's why the majority charge carriers are here holes, the holes are majority charge carriers, and minority charge carriers are electrons. Minority charge carriers are electrons. So the hole density is, because of holes are more, so that's why hole density is more greater than, much greater than the electrons density. Moles density is much greater than the electrons density. So that's why here the electron density is less than the hole density. So the acceptor level is close to the valency band because of holes are more. So that's why the acceptor, how much what is the border through the acceptor, this is the number of holes are there, so it is attracting more. So that's why accepting level is also near to the valency band, which is whenever electron comes to this place, and that can be accepted, not to reach the total valency band. It is electron is near to the valency band also, that can be attracted. So that's why the acceptor level is more. The effect of electrons is more because of it is having positive charge. If the positive charge is contained by the holes, p type of a, don't be confused, to better understand, to better remember, the p type means, p means positive type, positive means holes. We know that n type, negative electrons consist of negative charge. So that's why in n-type semiconductors, the electrons are majority charge carriers. Due to the electrons are majority charge carriers, so that's why that the donors level also will near to the conduction band because of electrons contained in the conduction band. So that's why the donor level is also near to the conduction band, and Fermi level also between the conduction band and donor level. Here that, though here n-type, in one word n-type we can remember everything. N-type means negative charge, n means negative charge, and as well as we can get that negative charge, and donor level is near to conduction band, and more electrons are majority charge carriers are electrons. Here is also p type of semiconductor. P type of a semiconductor means whenever the positive charge type of semiconductors. Positive charge means that is holes. Holes are majority charge carriers in p type of a semiconductor. Holes contained in the valency band. So that's why acceptor level which is near to the valency band. Acceptor level which is near to the valency band, and as well as the density of holes is more greater than the density of the electrons, and the Fermi level is lies between the acceptor energy level and valency band. Acceptor energy level and valency band, the Fermi level. The highest energy state that can be obtained by an electrons are called Fermi level energy. So this is about the distinction between the intrinsic and extrinsic semiconductors, and as well as the p type and n type of a semiconductors. There is a comparison and a distinction between the p type of, n type of, and intrinsic and extrinsic semiconductor. We are going to discuss about p-n junction diode. In earlier videos we discussed about the p type of a semiconductor and n type of a semiconductor. Now we are going to discuss about when a pure semiconductor like germanium or silicon is doped in such a way the one side of the semiconductor becomes a p type and another side becomes a n type. The p-n junction is formed, like whenever the p type and this is p type and this is a n type. Whenever the p type, whenever the sum of the material also combined, the p type of material and n type of material combined in a such a way, doped in a such a way, then the junction will be formed. p-n junction will be formed, and this is the two regions, the plane separating the two regions is called a junction. That is a p-n junction, means the p type of a material and n type of a material. This is the plane which is separating the two semiconductors, two planes, two regions. That is a positive. This is p type having the positive and n type having the electrons. In this case also, this p type of a material also consists of electrons also, but but the less quantity of electrons it is having, and also n type of a semiconductor is also having the charges of positive, but the less amount of positive charges. In case of the type, the symbol of a p-n junction diode is this one. This is a p type of a semiconductor, this type called a positive type, that is a p type of a semiconductor, and this one is a n side. This is the symbol of p-n diode, p-n junction diode. So here is that the arrowhead, this arrowhead shows the direction of the conventional current. The direction of the conventional, the arrowhead shows the, gives the information about the direction of the conventional current. Conventional current means the flow of the current. Then how this p-n junction is formed? The p-n junction diode is formed whenever the p type of a material and n type of a material combined, and it form a junction is formed between the p type and n type of material. Then the junction, that is p-n junction, the diode, which is the device which is formed, is called a p-n junction diode. In this case of, we know that p type of a material is having the majority charge carriers of holes, and n type of a semiconductor having the majority charge carriers are electrons. So that's why here the p type of electrons or holes are majority charge carriers. Due to that majority charge carriers are having by the p type and n type, some of the, whenever they are combined, due to the difference in concentration, because of it is having the positive and it is having the negative, due to the difference in, and some of the majority is having the negative, and in this p type of a semiconductor majority charges are having the positive. So that's why due to the change, difference in concentration, the deflection means there is a charge carriers will diffusing from one p side to one side to the another side, means the electrons are moving. Whenever they are combined, the electrons are attracted by the positive charges, and these positive charges are moved towards the negative charges. The diffusion will be happen from one side to the another side. So only those electrons are moved from the one side to the another side, which is the electrons are having the kinetic energy. The electrons which is having the holes are electrons, whatever they are. In the n type of semiconductor having the electrons, and positive in the holes, majority charge carriers are holes, so they jump from the, diffuse from the side to the another side, who's having the more kinetic energy, whose the electrons or holes having the kinetic energy, then only those can be transferred, diffused from their place to the another side. Then due to the diffusion, the current takes place. Whenever the charges electron is acquired the hole, and hole is moved to hole, due to this one the electrons are acquiring, the electrons are grab the hole, so then the current will be possible from p side to the n side, means from this side to this side the current will be passes from the p side to the n side of the crystal. So when because of the thermal energy, the diffusion is possible when from the p side to the n side, and due to the collision between the, means whenever the positive charges move from this place to the another place, and the electrons comes to this place to the another place, these are the electrons in this side, and positive charges or holes are in this side, then remaining holes cannot move from this place, because of there is a static condition barrier will be happen. Static conditional barrier happen because of due to the positive charge, the deflection will be possible, they won't allow to pass through this junction. And due to the electrons also, due to the electrons are in this side, moved from first ray of electrons moved this side, and in here is also electrons is there, so that's why whenever they are trying to cross this potential barrier, then the junction they won't allow to. So in this case of, the pair will be formed, the electron hole pair will be formed. So that electron pair will be formed, created, conduction of electron fills up the valent bond, means which are having the holes is acquired by the electrons, and fills by the destroying the electron, means destroying the electron and hole pair. Electron hole pairs are created, and due to the conduction, also conduction will be possible whenever by destroying the electron hole pair, then the covalent bond, the electrons will acquire the holes. by destroying the electron and hole pair. So that's why here, due to the whenever the electron and hole pair is formed, they can be sent inside the depletion layer. Inside depletion layer by the electric field is attached. By the electric field means whenever the electron hole pair are created, then the sent to the regions by electric field, sent to the regions by electric field inside the depletion layer, so the it constitutes the drift current will be possible. Means drift current means some of the due to the current which is flows due to the minority charge carriers present inside the p type or n type of materials. So that's why due to the drift current is formed from the n side to the p side, from n side to the p side, means due to the minority charge carriers, because of the thermal energy collision will be occur, because of when the p type of n type of material is added, means this is the positive side and these are the holes, these are the electrons. Whenever they are added to this is p type and this is n type, the electrons will diffuse from this side to this side and holes from this diffuse to this side. Then between the junction, the electrons grab the holes in the this side and holes comes to this side. The static condition will be possible, and which these positive charges holes do not allow to pass through the barrier until they have kind of more kinetic energy. So here is that the pair will be created due to the collision between this, and a pair will be formed. So here it is that the pair will be formed, and also the conduction of electron fills up the holes. Conduction of the electrons fills up the holes by destroying the plane, means the pair which is formed the electron and hole pair. So when electron and hole pair created, they sent to their regions. By electric field. Whenever the electric field is connected, the inside the depletion layer, this layer which is formed between the two regions, p type of a semiconductor and n type region, is called a depletion layer. In this depletion layer, some of the drift current will be possible from the n side to the p side. Starting whenever they are combined, due to the charge carriers are moved from the place to the another place from the other side, the diffusion current is in this direction from p to n. And here the drift current is passing from n to p, so that the drift current and diffusion currents are in a opposite direction. So in case of the steady flow, means if in case of the steady state, the depletion will be steady state, then both currents are equal in magnitude. According to the whenever the steady state, the PN junction diode is in steady state, the diffusion current and drift current are equal in magnitude. Then there is no transfer of charge. In the junction diode. This is about the PN junction diode and formation of a PN junction diode. Once again, when the pure material is doped in such a way, the one side becomes the p type of a material, p type of a semiconductor, and another side is n type of a semiconductor, is called as the junction is formed, that is PN junction diode. Or one PN type of a semiconductor and n type of a semiconductor combined and formed a junction between them, and the device which is created, the device which is formed is PN junction diode. Due to that one, whenever they are combined, near the junction, the electrons or holes are transferred from their side to the another side. Then some of the barrier will be formed, means that is called as depletion layer. At the depletion layer, the electron holes pair will be created due to the transfer of energies. And another thing, collision will be occur in the total PN junction diode, because of the charges are transferred from one part to the another part of the diode. So here it is that due to the diffusion means the electron is jumps from n type region to the p type region, and holes jump to in this direction, means electrons are required the holes. So that's why the diffusion current falls from p side to the n side. Same here, whenever the due to the thermal energy collision will be occur, due to the collision energy, the electron hole pair can be created. By destroying that created, the conduction will be possible. Also possible by destroying the electron hole pair, then conduction will be electron hole pair created, and a vacant bond destroying conduction of electron. So when electron hole pair created by descent to their region by electric field inside the depletion layer, by applying the inside by the electric field, then it will submitted into the depletion layer, sent into the depletion layer. So that's why the drift current will be, diffusion current will be means drift current will be flows from the N type of material to the P type, N side to the P side, due to the minority charge carriers. So here it is that in the steady state both the diffusion and drift currents are equal in magnitude, and there is no transfer of charge in steady state in the junction diode. This is about formation of a PN junction diode. The P type of a material and N type of a semiconductor, and as well as the formation of PN junction diode, it is also called as a junction diode. In P type of a material, the majority charge carriers are holes. In N type of a semiconducting material, semiconductors, the electrons are the majority charge carriers. Means due to the charge carriers, the current conduction will be possible in that materials. So that here there is some of the definitions we should learn about going to the forward discussion. Whenever the PN junction diode is formed, due to the charge carriers of in both materials, the diffusion current will be flows. Due to the diffusion current at the junction, some of the layer is formed. Some of the layer is formed on both sides of the junction. That layer is called as a depletion layer. That layer is called as a depletion layer. That is here when these are the holes and these are the electrons, whenever this combined means PN junction diode, this PN junction diode, then the negative charge carriers will move towards the P region, and the positive charge carriers means holes move towards the N region. At the junction, some of the small thin layer is formed due to the diffusion of charge carriers. Small thin layer is formed. That layer is called a depletion layer, and its thickness will be in order of 10 to the power of minus 6 meters. 10 to the power of minus 6 meters. That's why the definition is, due to the diffusion of charge carriers, a thin layer formed on both sides of the junction. In this layer, charge carrier becomes static due to mutual attraction force between opposite charges. Here, this is the positive charge, this is the negative charge. Whenever they are moved this side and they are moved this side, then here in the depletion layer, due to this one is the positive and this one is the negative, then the negative charges will not allowed to pass through this, and positive charge carriers means holes do not pass over through this, across this will opposes. So that's why here the condition will be in static, both will be in pair, whole electron pair will be static condition. So that's why here in this layer charge carriers becomes static due to the mutual attraction between the opposite charges. So that layer is called a depletion layer. So that's why the thickness will be 10 to the power of minus 6 meters. Due to the definition, in equilibriums, the opposite charge carriers accumulate at the junction. Opposite charge carriers accumulate at the junction, and for both sides of the junction. This produces electric field. This produces electric field. This electric field is called as a barrier electric field. Means this is the barrier. This is the barrier. So that's why the barrier electric field, due to the accumulation of the charge carriers both sides of the junction, electric field is produced. That electric field is a barrier electric field. So that this corresponds to the potential difference. Potential difference will be across the junction. Because of electric field is formed from this side, whole side to the electron side, more this side, means the positive side to negative side. So electric field is formed here P side to the N side. So this corresponds that P there is a potential difference across the junction. That potential difference is known as that potential barrier. That potential barrier. If the width is more increases, this potential barrier means this, if the depletion layer width increases, then potential difference also increases, then the potential barrier also increases. So that's why the potential difference across this, that V naught is equal to the ED, means electric field, potential electric field. So that's why it is for germanium. For germanium, that is 0.3 volts, and for silicon 0.7 volts. That potential barrier value will be 0.3 volts for the germanium and 0.7 volts for the silicon. So this is potential barrier. Potential barrier means, once again, in equilibrium, the opposite charges carriers accumulate. The opposite charge carriers accumulate on both sides of the junction. On both sides of the junction, this produces an electric field from P side to the N side. This is the P side and this is the N side. From P side to the N side means the whole side to the electron side. So that this corresponds potential difference across the junction is called. Potential difference across the junction is called potential barrier. It is denoted with V, and V naught is equal to the ED. ED means potential electric field. Then it is for germanium 0.3 volts and for silicon 0.7 volts. This is about potential barrier. By connecting this battery in such a ways, the depletion layer and potential barrier will be maybe decreases or increases. That can be PN junction diode can biased, means a PN junction diode can be connected across the battery into such a ways. Then its a depletion layer thickness may be increases in such a way and also decreases. That is called biasing of junction diode. By connecting the junction diode to the battery in such a ways, in two ways, those are biasing the junction diode. Biasing the diode into such a ways, their first one is the forward biased and second one is reversely biased. Let's see what is forward biased and what is reversely biased. So forward biased, when biasing the PN junction diode into such a ways, biasing a junction diode means whenever by connecting the battery to the PN junction diode, then that is called as biasing the junction diode. That can be possible in two ways. Those are the forward biased and reverse biased. So first of all, we are going to discuss about forward biased. Forward biased means here the P type of a semiconducting material, the P side is connected to the positive terminal of the battery, and N side of the semiconducting material is connected to the negative side terminal of the battery. Means in a PN junction diode, this will be the PN junction diode, this is the P type of a material, and this is the N type of a material in PN junction. So this P type is connected to positive terminal of the battery and N type is connected to negative terminal of the battery. So that when by connecting this positive terminal and a negative terminal in such a way, this is called forwardly biased. That is, in forward bias, the positive terminal of the battery connected to P side and negative terminal of the battery connected to N side of a PN junction diode. So by connecting this, if the external electric field is produced by the battery, already without connection of the battery, there is an internal connection, internal electric field is formed. Already we know that is EI is moved inward direction of holes towards the N side, means P side to the N side. By connecting the battery in forwardly biased, the external electric field is applied across the PN junction diode, so that it exceeds the internal electric field. It means more electric field is formed more than the internal electric field. So that's why here this is the positive terminal. So here is a P type of material is also having the positive charges, positive charge carriers, that is holes. So due to the repulsion between the two positive charge carriers, that positive charge carriers move towards the potential barrier, that is depletion layer, means moves towards the in this direction. Due to the same repulsion between the negative charge carriers in the n type of a semiconductor material and n type of a material, n type of the n terminal of a battery, negative terminal of a battery, then due to the repulsion between both of them, this negative charges also move towards the in this direction, towards the depletion layer. So due to that repulsion force between the positive terminal and the positive charged holes and negative terminal and negative charged electrons, the depletion layer width will be decreases. Depletion layer width will be decreases. So that here a current thus set up across the junction diode due to the diffusion charges. Diffusion of charges means the electrons move towards this direction, positive charges holes moves towards n type of a material. So that here the diffusion of charges, the current will be flows through the diode. Then the results, the depletion layer width decreases, so that the potential barrier is also, the thickness of the depletion layer decreases, and current, the negative charge particles move towards this direction and moves towards the positive terminal, and these positive holes move towards the in this direction, passes the current through the diode and moves in this direction. So that's why here if we draw a graph between the current and voltage, then potential, then the graph will be like this. At initial stage there is no much of increment of the current voltage, so that goes on, the current will be increases because of the thickness of the depletion layer decreases. Until the decrement of the depletion layer, the current will be flows normally. After the charge carriers, whenever we diffusion of this charge carriers, the depletion layer width goes on decreasing, and furtherly the current flows through the diode more and more. So that maybe the depletion layer width will be total decreases at the time, at some time, that will behaves like that there is no any depletion layer like that. So here we can say that whenever the charge carriers are moving across the junction diode slowly, diffusing from their region to the another region, then goes on increasing the jumping means it goes on increasing the diffusion, then the thickness will be less, decreases and goes on that, then the total depletion layer width totally decreases, and in some time it can be considered as there is no any depletion layer, means the potential difference will becomes zero. The total holes acquired by the electrons, so that's why I have moves in this direction, electrons will move towards the direction, the current flows in the total direction, will finally at the peak stage the current will be more and more, so that due to the forward bias the current will be flows in the circuit. So we can say that the graph is not linear, so that's why we can say that if the depth D is equal to means the thickness of the depletion layer D1 can be considered as this. If the D1 thickness of it decreases, then the potential V is equal to E into D1, E into D1, means the depends on the potential difference depends on the thickness of the depletion layer and the electric field which is applied and the internal electric field. So that's why some of the important points in that the forward current of the in order of milliamperes, means whenever that forward current will move in the milliamperes, and that the current flows due to the both charges, means due to the negative charge particles move this side and positive charge carriers will move this side. So due to the both charge carriers, current will be flows in the circuit, and also the variation of current is not proportional to V, means the V is not proportional to I in this case. So that's why here we can say that the graph is not linear. Linear means it is not move straightly, means it is not linear. This will be like in a curve path. This is the forward bias. Say about once again, when battery is the positive terminal of the battery is connected to the P side of a material, and a negative terminal of the battery is connected to the N type of a semiconducting material, then it will be the forwardly biased. PN junction diode is forwardly biased when the positive terminal of the battery connected to the P side of a material, and the negative terminal of the battery is connected to the N side of a material, then the external electric field is applied to the PN junction diode so that it is more than the internal electric field, so that the way here the due to the repulsion between the positive terminal of the battery to the positive charge, more holes more to the majority charge carriers which are placed in the P type of a material move towards the potential barrier due to the same repulsion between the negative terminal of the battery and the N type of a materials. Then holes moves, electrons moves towards the potential barrier, so that the potential barrier thickness will be decreases, so that the current will be set up across the junction diode due to the diffusion of charges. This one, the thickness of the depletion layer will be decreases, and as well as here the potential difference will be decreased, means the potential barrier is also decreases. If we consider D is the thickness of the depletion layer, then the potential V is equal to EI, means internal electric field, into D1. D1 is the thickness. This will be the potential, we can find it out. So that's why here in this case of forward current is in a milliamperes. Forward current is passed through the current is milliamperes, and current flows due to the two mobile charge carriers. These are the electrons and holes. Both of due to the both of the majority charge carriers, current will be flows through the circuit, and as well as in this the current is not proportional to the potential, so that why the graph is not linear. Whenever we plot the graph between the I and V, means current and potential, the graph is not linear. This is about forward bias. In earlier we discussed about the PN junction diode and its depletion layer, potential barrier. The depletion layer thickness will be increases or decreases by the connecting the external electric field, is nothing but connecting the battery to the PN junction diode. Before we discussed about that, the forwardly biased means when the battery positive terminal of the battery is connected to the P side of semiconductor, and N side of the N terminal of the battery is connected to the N type of a semiconductor, and it is forwardly biased. So the forwardly biased due to the attraction force between the positive and negative charge carriers, which are holes and electrons, the depletion layer thickness will be thinner, means decreases, so that the conduction is means current flows through the diode due to the both mobile charge carriers, majority charge carriers, both mobile majority charge carriers. In that case of the terminal, means whenever it is flowing, the current goes on increasing the electric current in the junction diode. Finally it will rapidly increases. At that some stage we can define that the depletion layer will be totally decreases. So here now we are going to discuss another one, means the another bias, that is the biasing of PN junction diode in reversely, means reverse bias. What is meant by the reverse bias? Here the P type of a material, N type of a material, means PN junction diode. This is the PN junction diode. Then here whenever the PN junction diode, the negative terminal of the battery is connected to the P type of a semiconductor, P side of a semiconductor, and positive terminal of the battery is connected to the N side of the semiconductor, then it is reversely biased. Reversely biased. To better remember, we are connecting reversely, means it is the positive charge, majority charge carriers are the positive, so that's why positive connected to the negative terminal of the battery. And here we can say that the negative charge carriers are there, so that's why we connected to the positive terminal of the battery, means we connected reversely. So that's why it's a reverse bias. Due to that reverse bias, by connecting the external battery or external electric field will apply to the junction diode to help the internal electric field which is produced due to the connection the P type and N type of a material. So here the internal, to help the internal electric field, external electric field is applied. So due to this one, the majority charge carriers are prevented to cross the junction, means they cannot cross the junction, unable to cross the junction, because of here the negative charged particles are there, the positive terminal is applied in this direction, and positive terminal of the battery and connected to in this direction. So the negative terminal is connected to in this direction. So that's why here the positive charges will majority charge carriers in the p type of are positive charge carriers. So that's why they will move towards this direction, towards in this direction. So towards the negative direction, and also due to that the electrons having the negative charge carriers will move towards this direction. So towards the positive terminal of the battery. So that's why the depletion layer width is more thicker, means increases. Depletion layer width increases due to the minority charge carriers are forced to move across the junction, means in this case of minority charge carriers in the n type is plus, means holes, and in the p type of a semiconductor the minority charge carriers are electrons. So that's why due to the minority charge carriers will cross the junction, or push to cross the junction. So the current is flows in the connection through when reverse bias. So that's why due to the minority charge carriers the current is passing through the junction diode. So that due to the in reverse bias, so that's why it is called a reverse current. It is a reverse current. By the connection of the majority charge carriers are prevented to cross the junction, and so that the minority charge carriers are pushed to cross the junction, so that the current flows through the junction. So that the current is called as a reverse current. So that the thickness of the depletion layer increases, so that the potential barrier is also increases. So that the conduction means the current flows through the junction diode in reverse bias due to the minority charge carriers. Whenever the minority charge carriers move towards in this direction at the junction, the reverse current means here the total negative charges moves towards in this direction and total positive charges moves in this direction. Then means either the positive charge carriers move towards the battery terminals, and here the positive, whenever the positive terminal taken this, the current will suddenly increases due to the reverse current flows through the junction. The current suddenly increases, the breakdown at the junction. The breakdown is happened at the junction. So that the breakdown will be happens at the junction due to the reverse current. The current voltage increases. The voltage increases abruptly. So that's why that will be breakdown. At that sub voltage, when the abruptly voltage increases, that breakdown is called as a avalanche breakdown. So here is that in this case of reverse bias, when the reverse biasly connected PN junction diode, the current flows, reverse current flows in microamperes due to the minority charge carriers in the both side of the semiconductor materials, so that the current will be flows in the diode. So that's why here within the diode, here is also the current will be, the graph drawn between the current and voltage will be non-linear. The VI graph is a non-linear. Once again, reverse bias means here the negative terminal of the battery connected to the P side of a semiconductor, and positive terminal of the battery is connected to the N side of a semiconductor. Then here the connection is called reversely biased, so that the external field is applied to help the internal field which is already applied in the body, in the junction diode. So that's why here the majority charge carriers are prevented to cross the junction because of the positive charge carriers move in this direction to attraction between the positive and negative terminals, and the negative charge carriers are electrons are moved towards the positive terminal of the battery. So that's why the depletion layer width means the thickness of the depletion layer increases. So that's why potential barrier is also increases. If the D2 is the thickness of the depletion layer, then the potential barrier will be V is equal to EI D2. EI is the internal electric field. So here the reverse current is in order of microamperes, and one more thing is here the potential difference will be increases. The potential, due to the potential difference increases, and finally at some stage at the junction that will be due to the reverse current, the rapidly the voltage increases abruptly. So that's why the breakdown is called as avalanche breakdown. The breakdown is called avalanche breakdown. This is about reverse bias. Now we are going to discuss about the characteristics. Means we know that voltage is proportional to current. But in this case of some of the cases, in the forwardly biased connecting and reversely biased connecting, what is the current to voltage characteristics of a PN junction diode? Let's see. What is the characteristics of a current voltage characteristics in a forward and a reverse? Characteristics of current voltage means a variation of IV characteristics. Current to voltage, whenever the current passing through the diode, when unbiased or biased and reversely biased, forwardly biased and reversely biased, then what is the variation between current and voltage? We will see here the graph plot between the voltage and current. Here is this is the voltage and current, means according along the x-axis voltage has taken, along the y-axis current has taken. First of all, unbiased means whenever the current unbiased, this is the p side of this is on the n side of the semiconductor, then unbiased the dB the depth of the thickness of the depletion layer, means whenever the current is flowing through the circuit, then so somehow after some time they will be constant flowing through the circuit, the voltage will be happen. Means here when the started to hear the knee voltage, here the voltage which is across the potential barrier, means depletion layer which is crosses the depletion layer. After the connection of whenever we say increase it, that the current will increase rapidly. After some of the crossing the potential barrier, depletion layer goes on increasing, then the current will be flows into sometime depletion layer width will be less, means the thickness of depletion layer will be decreases. So that's why the more current means more charges, mobile charge carriers are crossing the potential barrier. So that's why the more current flows through the circuit. So that's why the current will increases abruptly, rapidly through the forward bias. So that's why that voltage will be positive, but there is some low. In a forward bias, the voltage will be positive and the voltage will be low. So that the final current is I naught is equal to e power EV by kT. K here, K is the electron, EV means electron volts, K be the Boltzmann constant, which is having the value of 1.38 into 10 to the power of minus 23 joule per mole Kelvin with the in forwardly biased, means when the current flowing through the circuit, then to cross the depletion layer, below the depletion layer crossing the movement, means the current flow will be not increases rapidly, it will move with the voltage. It will move with the voltage also beyond the knee voltage also, there is no any increment, means there is no not in the linear, that will not increase with the voltage. So that's why this is not linear. So after some crossing the potential barrier or depletion layer, the more mobile charge carriers are ready to cross the potential barrier or a depletion layer, then the current flows abruptly, means rapidly increases. At that means it is the forward voltage beyond which the current through the diode starts increasing. Current through the diode starts increasing. From that voltage, the current starts increasing in the diode. That forward voltage is called as a knee voltage. That forward voltage is called as a knee voltage. Means at this voltage, the forward voltage, the current is increasing in the diode. The current is passing through the current passing through the diode starts increasing in the diode is called a knee voltage. Means that will currently rapidly increases. The current will rapidly increases in the forwardly biased. So that's why that will be the knee voltage of, that is called as knee voltage. The forward voltage beyond which the current passes through, the junction starts increasing rapidly with voltage is called as a knee voltage in that case of. Means whenever the forwardly biased, the thickness of the depletion layer decreases. It is unbiased, less than the unbiased, the depletion layer with decreases. So that's why here some rapid increment of current is there. So here it is that this is the voltage After this voltage will be constant, the voltage, there is no increment of voltage. So that's why in forward bias the voltage is positive, but it's a low. If in case of a reverse bias, if we come for the reverse bias, due to the minority charge carrier, some of the small current flows through the diode, that is a reverse current. That is the less amount of current flows through the circuit. So that's why this is the less amount of current. The less amount of current circuits abruptly at some of the volt breakdown, at the sum of the voltage, at some of the voltage. This is the avalanche voltage, we can say that the Zener voltage, that is also called as a breakdown at that voltage. And reverse bias means after taking the so many voltage, after that there is a negative and voltage will be high, the potential will be high, the potential will be high in reverse bias, then the current voltage is more sufficiently high, and also same thing here, the at some of the voltage the covalent bonds near the junction breakdowns, means whenever if we take the PN junction diode, the depletion layer width increases, the depletion layer width increases. Wherever this at the junction the covalent bonds near the junction breaks down, also large number of charge carriers are produced, means due to the sufficient high voltage, the sufficiently high voltage, so that the covalent bonds near the junction diode, near the junction break down, and also produces large number of charge carriers are produced within. Then the reverse current increases abruptly, suddenly the current will be increases, suddenly the current will be increases. So that breakdown is called as, whenever the covalent bonds are breaks, that breakdown is called as. At that breakdown the reverse current flows rapidly, changes the current, the reverse current rapidly increases, that is called as, that breakdown is called as avalanche breakdown, avalanche breakdown. If the reverse bias voltage is made sufficiently high, means whenever the reverse current is flowing, the current will be, the voltage potential will be high in the diode. At that high voltage, at the potential junction the covalent bonds breaks down, and so that the reverse current will rapidly increases, abruptly, suddenly increases. So that's why the suddenly increment of the current is called as, that breakdown is called as avalanche breakdown, means more than the depletion layer width will be increases, so that whenever it will take more time to increase, more time to increase to remain constant. So that's why here the voltage will be negative, voltage will be, this is the negative side, so that's why voltage will be negative, but high voltage is there in reverse bias. So that's why the reverse current I naught is equal to IR is equal to minus I naught. That is the about the VI characteristics, means current voltage variation of characteristics of whenever the current flowing through the diode in forward bias and in a reverse bias. After forward and reverse bias of the PN junction diode, means biasing the PN junction diode, now we are going to discuss about the rectification. Here what is meant by the rectification? Rectification means here the current, alternating current is converted into the direct current, so that the usage of home appliances, whatever the electronics get, would not damage due to the alternating current. The process of conversion of alternating current into direct current is called a rectification. A device which is used to rectify or convert a conversion is called a rectifier. So here that in that rectifier we will use that the PN junction diode for this rectification purpose by tapping center tap transformer, by connecting the transformer, then we can get that here the rectification means the conversion of alternating current into direct current is called as a rectification. And also that is also a device which is used for the rectification is called as rectifier. It may be two types. One is by using the one single diode that can be constructed like this. This will be the half wave rectifier, half wave rectification. The process is going on in this device is a half wave rectification, and this will be the half wave rectifier. In this rectifier, this is a load resistance, RL denotes the load resistance, and RF will be the forward resistance, which is internal resistance of that circuit or diode, which is the internal resistance of the diode, that is RF means forward resistance. And also here the PN diode is used, and the P side is converted. This will be the transformer, and this is alternating current is given through the transformer to the diode, to the circuit. So that here P type of a transformer is connected to the end A of the transformer, and N type of another is connected to the load resistance. Between the transformer, the RL load resistance, what we can get the output here. Here we can get the output by giving the alternating current from this signal, then we can get the load output from the load resistance. In this total rectification, current will flow. In this current will flow in the load resistance during only the positive off cycle, means whenever the current is alternating current is supplied to this, then that will be the taken in the half cycles, that is forward. This one is the positive half cycle and negative half cycle, positive half cycle, negative half cycle. In this type of signal, it can be given to the diode in the off wave rectifier, so that only whenever the positive cycle given to as input to the circuit, then we can get the positive output. Otherwise there is no any output. What is that? Let's first of all see. Therefore here current will always flow only in one direction, that is whenever the positive cycle DC output when get, means current will only travel in only one direction only, either from P to N only. Then only that diode can be forwardly biased. In this forward bias, the conduction will be happen, means current flow through the diode. The depletion layer width can be decreases, so that the current will flow through the diode. So here whenever it is connected, the ideal diode is connected in circuit and input AC with a transformer. This is AC transformer, and also diode is connected to this one. Then finally to get the output, the load resistance is connected. In this case, when the input signal, the positive off cycle given to this, at end of the transformer, this will be the positive off cycle, means the current flowing from the A end to the this one, means P to N, like this, the current is flowing like this. So that's why this will be the from P to N, in the direction of the P to N. Whenever they are moving in P to N at A end of the transformer, this binding becomes that positive with respect to B. This will be binding will be positive with respect to B. This makes this will be the forward bias. In the forward bias, the total majority charge carriers move in this direction, and at the same time the N opposite direction will move. The depletion layer width will be decreases. Then so that's why total data becomes positive with respect to B. So that way this diode forwardly biased. This can becomes a forward biased. So that diode can be accept or allow the current to flow through it one. And during whenever the negative off cycle is given, means the negative off cycle is in like this, means here the negative off cycle is in like this, means whenever the current flowing through this one, means during the negative off cycle, end A becomes negative. This whenever the positive off cycle is given, it end A becomes a positive, and whenever the negative off cycle is given, that end A becomes a negative. So that whenever the negative becomes, then it will be becomes a reversely biased. The P type of a connection connected to the negatively, and N type of a connection connected to the positively. Then it will becomes reverse biased. In this reverse biased, the depletion layer width is increases. The depletion layer width increases. So that's why here the PN junction diode could not allow the current to through it. So that's why here will be current do not flow, so though we don't get the any output from here, only the space we can get, means the empty. That means whenever the positive half cycle is given, the at end A becomes positive, the binding becomes positive. So that's why this allows PN junction diode becomes whenever this total binding becomes forwardly biased. So that's why the current allows through the PN junction diode the current flow in the circuit. So that's why output we can get that the RL is a positive half cycle we can get. And also when the negative half cycle, means during the negative half cycle in opposite direction it will travel, means the NDA becomes negative. Whenever it is becomes negative, the p type of a semi in the PN junction diode, p side connected to the negative terminal of the transformer, then it will becomes reversely biased. So whenever it is becomes reversely biased, the depletion layer width will be increases. So that's why here the current do not flow through the diode, and diode will not pass any current. Therefore the current flows in the load resistance during each positive cycle only. Then we can get that. Here is the sine wave we can get. Sine wave we can get. So that's why here I current is equal to, we know that I is equal to V by R, the voltage by resistance. So voltage will becomes V naught sine omega t plus pi, means here the sine waves we can get, V naught is the voltage, then RL plus. The here we have two resistances is there, one is a load resistance and another one is a forward resistance, means the diode resistance. What the diode internal resistance, that will be RF, we can get the RF also, or the R diode, means that is a load resistance or a load means resistance, diode resistance. So that's why we can get that current I is equal to V naught sine of omega t plus pi by RL plus R diode. That means the current, if we want to calculate the current, only whenever the in positive half cycle, this will happen only positive half cycle, the current I is equal to V naught sine omega t plus pi by RL plus RF or R diode, means that is RL means load resistance and R diode means internal resistance of the diode. Then we can find out that the efficiency, how much the efficiency that can be happen, means the how much the current, how much percentage of current efficiency that half wave rectifier, means how much the percentage of current can be transferred from alternating current to the direct current, means 40.6% of voltage can be converted from alternating current from the direct current. So that's why we can get that the output by input, means the efficiency is equal to the voltage output by voltage input. Then we can get that here, that is the efficiency will be neta, it will denoted with the neta. So that's why neta is equal to 40.6 into RL by R diode plus RL, means here 40.6 of the current can be transferred, means converted in half wave rectifier whenever the RF by RL which is tends to 0, means internal resistance by load resistance, whenever this which is tends to 0, then that can be neta is equal to the efficiency of half wave rectifier will be 40.6% of the current can be converted from alternating current to the direct current by using the half wave rectifier. This is the one of the most important question for the IP purpose. Most of the times we got this question, so we must read carefully. Then once again we will repeat this. Half wave rectifier means what a rectification means the conversion of alternating current into the direct current is called as, the process is called as rectification. The device which is used to convert the alternating current into the direct current is called a rectifier. This rectification process can be done in two ways, by using the half wave rectifier and at the same time a full wave rectifier. In this case of half wave rectifier means we will use one PN junction diode in the half wave rectifier, so that it is connected to the transformer, which is the input AC signal is there to the transformer. We will supply to the current, alternating current to the diode, and at the RL means load resistance, at the load resistance we can get that potential output, we can get that. So during the positive half cycle only that PN junction diode will allow the current, so that's why during the half cycles only the current passes through the circuit. In this case, first of all, here we will discuss the construction, how do we construct that one. A ideal diode of PN junction diode is connected to the another part A, and another this one, the N type of a connector is connected to the output, from that's the connected to the B. Then whenever we give the positive half cycle to the PN junction diode from the input AC, input alternating current through the from the transformer, then the positive half cycle will whenever it is during the positive half cycle, the at end A will becomes positive, and A becomes positive, means the started from the positive cycle, so that's why it will becomes positive. Otherwise it started at negative, then it will becomes negative. So that's why here whenever the positive half cycle given that, then the A becomes positive, then positive is connected to the P type of a diode, then that will be forwardly biased. Forward biased means when the P type P side of a junction diode is connected to the positive terminal of the battery, and N side of the diode is connected to the negative side terminal of the battery, then that is forwardly biased. So that in case of whenever A becomes positive, then it is forwardly biased, so that the current the PN junction diode allows to pass the current through it. Because of the depletion layer width will be decreases in forward bias, so that's why conduction is allowed by the PN junction diode, so that we can get the positive half cycle. Otherwise, second one is whenever we give the during the negative half cycle, during the negative half cycle we can get that end A becomes negative. Whenever end A becomes negative, then that is a negative terminal of the transformer is connected to the P type of P side of a semiconductor, means reversely biased. That it becomes reversely biased. In that reversely biased, the current do not allowed by the PN junction diode. Due to that, the depletion layer width will be, means potential barrier width will be increases. So that's why due to the minority charge carrier, some of the flow of the current will be happen, but that will be negligible in the circuit due to the internal resistance have by the PN junction diode. So that here during the negative half cycle, the end A becomes negative, so that it is reversely biased. There is no current flow through the diode, so that's why here current flows in the load resistance whenever only the positive half cycle input is given. So that whenever the positive half cycle is given to the input, then current I is equal to V naught sine of omega t plus pi by RL plus R diode. Means here the RL means load resistance where we can get the output, and R diode means the internal resistance with the diode. So that's why here then efficiency, if we want to know the efficiency, neta is equal to 40.6 load resistance by RF plus RL. Here RF means internal resistance by the, this is forward resistance we can get, we can see. So this is load resistance. During this one 40.6% of the current 40.6% of the current can be converted by using the half wave rectifier. This is about the half wave. So after knowing about half wave rectifier, means the rectification of a PN junction diode, by using this the alternating can be converted into the direct current by using the rectifier. In that rectifier we discussed about the half wave rectifier, means by using the one single diode, whenever the positive half cycle given to AC signal given to the PN diode, then only we can get the output, DC output, that is the form 40.6%. Now we are going to know the second way of rectification, means whenever the alternating current given to the diode, then the circuit, then it can be converted into the direct current by using this in the full wave rectifier. Full wave rectifier means in this the current flows through the load resistor. Current flows through the load resistor in the same direction, for both of the diodes, what both of the cycles, that is either positive cycle or a negative half cycle, the current will flow through the load resistance in a same direction. Let's see how it will be. This full wave rectifier consists of two diodes. This is considered as D1 diode, and this can be D2, diode 1, diode 2, P, N, positive, negative. So here when the signal given to this by using the center tapped full wave rectifier, this is also called as center tapped full wave rectifier, means here the load resistance is center tapped, means here center tapped at O, means here the two diodes of D1 D2 is connected across the two ends of the transformer for the secondary winding of the secondary. This is the primary winding and this is the secondary winding. Across the two ends, two diodes 2 can be converted in this way to to the secondary winding of the transformer. A load resistance is connected center tapped at O. Center tapped at O means the D1, D2 diodes are connected for the secondary winding, and the output load resistance is connected center tapped at point O. Then whenever during the, let's come for the operation, means how the operator can be converted. Whenever the positive off cycle given to this, means whenever the signal given to this, then that will be the sine wave, that is a positive or negative, positive, negative, means alternating current, maximum minimum current can be passed. Means alternating current means whenever the current oscillates, when the current oscillates maximum to minimum, then that will be the alternating current. So that's why here positive off cycle, negative off cycle, we can get that from the input. Whenever it is given to this, then we know that the positive off cycle given that, then here it is that end A becomes a positive, and A becomes a positive, and whenever this B and B becomes a negative, and B becomes a negative. So that's why here whenever PP connected to this, means forwardly biased, means a positive terminal, means NDA is the positive, becomes positive, the P type side of a diode, D1 diode connected. So that's why it will be forwardly biased. Whenever it will becomes negative, then here the P side of a junction diode is positive, and it will be connected to this. This will becomes reversely biased. Means during the positive off cycle, the D1 diode is made forwardly biased, and D2 will be becomes reversely biased. During the positive off cycle given in full wave rectifier, the D1 diode becomes forwardly biased, and D2 diode becomes reversely biased. Due to that one, it here A becomes positive whenever the positive off cycle given, then B and B becomes negative, so that it will becomes reversely biased. So that the conduction, means current flows through the D1 diode, that the output move in the same direction. The output at the load resistor, we can get the output through the current passing through the D1 diode. So that's why whenever the positive off cycle is taken, then due to the D1 diode, the current passes through the D1 diode, we can get the positive off cycle, means output we can get. Here during the negative off cycle, means whenever the negative off cycle taken, then during the negative off cycle, this will be the movement. During this one, here the B becomes positive. B becomes positive, means either if we take that whenever it like this, then here whenever the negative off cycle started, then next to here A becomes negative and B becomes positive. For the negative off cycle, A becomes negative and B becomes positive for the secondary winding. So that here whenever the A becomes negative, the A end connected to the D1 diode, the P side of a D1 diode, means this is negative and P diode will be positive, means like that will be the reversely biased, means whenever the negative off cycle at the A becomes negative, so that the D1 diode becomes here D1 diode becomes reversely biased, so that the D2 will be in a forward bias. So that due to the forward bias, D2 diode is forwardly biased, current flow through this D2 diode. Then here we can get the output due to the D2 diode for the negative off cycle like this. See, whenever the negative off cycle we taken, then we can get the due to the D2 diode, the current will flow through the circuit, then output we can get continuously like this. Another positive off cycle, then we can get the negative. Here this, in both case, the current in load resistor is in same direction. Either D1 is in positive forward biased and D2 is reversed, either D1 is reversed and D2 is forwardly biased. Then current flows through the load resistance, we can get the output at load resistance in the same direction for the both off cycles, positive off cycle and negative off cycles also, input of AC, then we can get that. Then the efficiency can be 81.2% of the current can be converted by using the full wave rectifier. 81.2% of current efficiency of if it 81.2% of efficiency is there for the full wave rectifier. So that here mostly we will use this one. Once again, full wave rectifier is also connected whenever the two centrally tapped full wave rectifier. We can say that center tapped full wave rectifier. This is load resistance is centrally tapped at the transformer at point O. Here in this full wave rectifier we use the two diodes. They are the D1 and D2 diodes are connected at the secondary winding ends of the secondary winding, that is A. D1 diode is connected at the A and D2 connected at the B. So that here in this case the current will flow in the load resistance is in the same direction for both off cycles D1 and D2. Whenever the two diodes are connected in this, then we can get that it consists of D1 and D2 connected. For the positive off cycle whenever we give, for the positive off cycle when we give that, then the A end becomes positive and B becomes negative. So that the D1 diode is forwardly biased, becomes forward biased, and D2 diode becomes negative, means reverse bias. So that the current flow through the D1 diode, so that way we can get that due to the D1 diode conduction current will flow through the D1 diode, then we can get the output. So that's why here output will be here indicated that is due to the D1, and whenever the negative half cycle given, then A becomes negative and B becomes positive. So that the D1 becomes a reverse bias and D2 becomes a forward bias. So that's why again we can get the output in the same direction. Same as here positive half cycle we can get, here negative half cycle is also output we can get. So that's why forwardly biased we will use the two diodes which is working alternatively. When the D1 is forwardly biased, D2 will be in reverse biased. Either D1 is reverse biased, D2 will be in forwardly biased. So that we can get the output alternate normal equally whenever the alternative signal is also given, means alternating current given to the circuit. Due to that alternating working of the two diodes, we can get the result in that efficiency 81.2% of efficiency of a full wave rectifier. We know that the efficiency formula neta is percent is equal to 81.2 RL by RL plus RF, means here the RL means load resistance, RF means the forward resistance which is having the diode. So that's why it will depends on this one. The 81.2% of efficiency there when the RF by RL is tends to 0. R by RL is tends to 0. This is about a full wave rectifier. Once again here that during the positive half cycle of AC, the NDA of the secondary winding becomes positive and B becomes a negative. So that this makes a D1 forward bias and D2 in reverse bias. Therefore, D1 allows current while D2 does not. Whenever the positive half cycle, D1 allows the current, D2 does not. Then thus current is load resistance RL will come through the D1, so that we can get the output due to the D1. In reverse bias means in the negative half cycle, during the negative half cycle of AC, NDA of the secondary winding becomes a negative, so that the D1 is reversely biased and D2 will be forward biased. So thus current of load resistance will pass through the D2 only. Thus current in load resistance will pass through the D2. Therefore the current in load resistor is in the same direction for the both half cycles in a full wave rectifier of input of AC. Then efficiency will be 81.2% of efficiency we can get from the full wave rectifier. This is about rectification of junction diode. It can be two ways, that can be rectification will happen two ways, that is a full wave rectifier as well as a half wave rectifier. Diode. Zener diode means, already in earlier videos we discussed about that PN junction diode means whenever the two P type of a semiconducting material and N type of a semiconductor material is doped, then we can get the PN junction diode. Then what is Zener diode? Actually, what is the use of Zener diode and why do we need a Zener diode? Means whenever the PN junction diode is connected into different bias, means either forward bias and reverse bias. In forward bias, due to the repulsion between the positive terminal and the positive P type of a material, due to that the conduction depletion layer which will be decreases. then due to the majority charge carriers in that type of materials will move to the another region, will move into the another region due to attraction between the two opposite terminals, opposite charges. So here, in case the PN junction diode is connected in reverse bias, due to the attractional force between the positive terminal of the battery to the negative side of, means N side of a semiconductor, and negative terminal of the battery and P type of semiconductor, means this if reverse biased. Whenever the reverse biased, due to the minority charge carriers, a small current will flow through the circuit. So due to that, the depletion layer will be increases, then the potential barrier is also increases. We can get the output is nil, means there is a zero output we can get, and also due to the sharp breakdown will be happen due to the minority charge carriers, that junction will be breaks down. So due to avoid that breakdown, to the keep the voltage at constant, we just need a Zener diode. Zener diode means a scientist named C. Zener has invented this Zener diode. He did the experiment by using the PN junction diode is heavily doped, means the PN junction diode is heavily doped on both sides, either P sides and N sides, by the impurities that can be changes. The reverse current is having increases sharply. Whenever the PN junction diode is doped heavily, then the Zener diode can be formed. Due to the doping heavily, the reverse, means reverse current having this, the reverse current is increases sharply. So that's why here it can operate the system continuously without any damage. So here it is that the Zener diode can be used to run the junction without damaging the circuit, to keep the constant voltage. Zener diode can be used, that can be operated in a reverse bias only. If in case of this, the Zener diode can be connected in a forward bias, that is also can be act as a normal PN junction diode. Whenever we connected in reverse bias, then the Zener diode can be it like ordinary diode, except that it is a heavily doped, so that have sharp breakdown voltage called a Zener diode. Means it is having the sharp breakdown voltage. Whenever it is heavily doped, the diode is having very sharp breakdown voltage. That breakdown voltage is called as a Zener diode. And also this diode, this is the symbol of the Zener diode, whenever the same as PN junction diode, but the N side of a material, this P side of a material and N side of a material. N side of a material is can be denoted as a curved like Z. Z means Zener, like Z. Z means that's a Zener. It can be denoted as this symbol of Zener diode. This is the symbol of Zener diode, so that it can be operated in reverse bias only. Always it can be operated, must be operated in a reverse bias only. Whenever it is reversely biased, then it is having the diode will having the sharp breakdown voltage, so that it can be called as Zener voltage. And Zener diode is always used in a reverse bias, so that it is also used for the voltage stabilization, means as a voltage regulator or voltage stabilization. To stabilize the voltage, it can be used, like nowadays we are using the voltage stabilizers for the electronic gadgets. If we get the more current into at home, then that can be passed through it constant supply to the electronics, TV or fridge or whatever the electronic gadgets, to avoid the breakdown, to avoid the short circuit, to avoid the damage. So we will use the stabilizers. That is the voltage stabilizers. In that voltage stabilizers also we will use a Zener diode. So in case of, by using this here, whenever it is forwardly biased, it is act as a normal PN junction diode. Whenever it is connected in reverse bias, it is flowing through this. It is independent of, means whenever the voltage across the voltage, drop the voltage across the Zener diode, it is independent of the current flowing through the diode. So that way voltage remains constant. So here it is also, whenever the voltage is moving like this, then current, whenever the voltage potential drop across the Zener diode, then the current will independent of the current. So that's why it will be constant current flow will be occurs. So here the Zener diode can be used as a voltage regulators to stabilize the voltage, to keep the voltage at constant. The voltage regulator means Zener diode is a voltage regulator or voltage stabilizer. This is the circuit of a voltage stabilizer. Here this will be Zener diode, this is P side, this is N side. When the current is connected, can be connected in reverse bias. So that's why the P type of a material can be converted to the negative terminal, and negative N side of a diode can be connected to the plus terminal. So whenever this is connected, then here the current flows already, we know that this positive terminal to the current flows, that is IZ is the Zener current. The current which is flowing through the Zener diode is called a Zener current. So whenever it is passing through, whenever this current is flowing and so another current is also flowing through it, then this will be the load current, and the current, total current will be, means here I is equal to IZ plus IL can be calculated. So that's the flying current moving like this. Then the output voltage can be taken at the V out, that is RL resistance. That is VZ, we can get the output. So that Zener diode used to get a constant voltage output from source when whose voltage may vary over a wide range. Means whenever the large potential drop across the Zener diode, then the Zener diode will allows the current constantly without any increasing, decreasing. The flow will be, the current will be constant. So that's why we will use the Zener diode as a voltage regulator. And also arrangement of the Zener diode. Zener diode means here the Zener voltage Vz is connected across the load resistance. This is the load resistance, right? So across the load resistance RL, across which is constant voltage desired. Here the constant voltage which can be desired. So that's why when input voltage varies, means increment on decrement of means whenever the alternating current given to the system or circuit, then the input voltage will be varies. The Zener diode changes its resistance by creating the charge carriers in the diode. When the input is given to the system or input is apply alternating current is whenever connected to the system, then the Zener diode will create the mobile charge carriers. In that case mobile charge carriers, so that it can be changed its resistance as per this, by creating the charge carriers it keeps the voltage at constant. So that's why here when input voltage varies, the Zener diode change its resistance by creating charge carriers inside and keep voltage constant. That means here whenever the alternating current is applied to the input, then we can get the output will be remains constant, because of here this will resist the flow of more charge. Other than the keeping the constant voltage, it cannot be allows the more voltage through it. So that's why here the Zener diode can create the more mobile charge carriers which is equal to the Zener voltage means it gives the constant current. If we get that whenever the voltage is more, then if whenever the electronic devices which are connected to stabilizer, the electronic gadgets could not damage, because of the stabilizer will stabilize the voltage which is connected to the electronic device or home appliances, and so that can be stabilized. If we get the more current through the pole, from the pole wire, then that cannot allow that much of current to passing to the home appliances, electronics. So that's why that is the stabilizer. Stabilizer means it stabilizes the voltage. So here that the Zener diode uses as a voltage regulator or voltage stabilizer. In circuit, this is RL is connected parallelly, so that output we can get it is really equal to the Vz. Either we can get that, here is also we can get like this also. Here is that also we can get the output. Here we can get the output. This is the load resistance and this is the input. This is about a Zener diode and why the Zener diode uses as a voltage regulator or a voltage stabilizer. Once again, the heavily doped PN junction diode on both sides and P sides and N side can be known as Zener diode. Due to that heavily doping, the diode will having the reverse current will increases sharply, means that breakdown is having that sharp breakdown will be having, then the voltage having that sharp breakdown voltage, that voltage is called as a Zener voltage, and this is the symbol of a Zener diode. And also Zener diode must be connected in reverse bias, because of whenever the diode is connected in reverse bias, then only we can get the sharp breakdown voltage, otherwise it can be connected in forward bias, the PN junction, which allows the flow of current, or which it will be their voltage we can get. But in case of reverse bias we cannot get the voltage, so that's why it must be connected in a reverse bias only, so that to keep the voltage at a constant. So that voltage stabilization purpose, means what is voltage stabilization, means the device which is used to stabilize the voltage, that is called as voltage stabilizer or voltage regulator. This is Zener diode can be used as a voltage regulator. This is the circuit diagram. Across the Zener diode, the input is parallelly connected and output is also load resistance. The output is also connected parallel to the load resistance. So that the Zener diode is connected reverse bias, because the positive terminal of the battery is connected to the N type of a semiconductor material, and a negative terminal is connected to the through the external resistance R, we connected to the P type of a material. So that here whenever the Zener diode can be connected, when the alternating current is connected to the circuit, then by changing the resistance of the Zener diode, by creating the mobile charge carriers inside, it changes its resistance and which does not allow the more voltage through the Zener diode. So that keeps the current will independent of, current is flowing through the Zener diode is independent of the potential drop or voltage drop across the Zener diode. So that's why here the constant voltage can be kept by the Zener diode. So that's why that Zener diode used as a voltage regulator, means to the reverse current increases sharply without damaging the diode. So here to continue without damaging the diode, Zener diode uses as a voltage regulator. When input voltage varies, the Zener diode its resistance changes, and by creating the mobile charge carriers and keeping the voltage at constant. So that's why here in circuit RL means output voltage is connected, RL is connected parallelly to the output voltage, so that output voltage will equal to the Vz, which is a constant. This is about a Zener diode, and Zener diode used as a voltage regulator. After knowing about the Zener diode and which is connected in reverse bias, now we are going to discuss about optoelectronic junction devices. Means what is meant by the optoelectronic junction devices? Means whenever the optical light, means what we can see the light like sunlight, whenever the light is incident on the devices which is photosensitive semiconductors, the material which is made up of is photosensitive, semiconductors are made up of with photosensitive materials, then that will be the photosensitive, means semiconductor diodes in which carriers are generated by photons. Photons means whenever the sunlight is incident on the some of the photosensitive substances, plates, then due to that generated, means carriers means charge carriers are generated by the photons in the semiconducting materials like diodes, in junction diodes, semiconductor diodes, then that will be the optoelectronic junction devices or photo devices. So, photosensitive devices. So, in this case of 3 types, it can be classified into that. They are that first one is a photodiode, which is detecting the optical signal. Photodiode can be detected the optical signal. The next one is a light emitting diodes, LEDs, light emitting diodes. Whenever the light is incident on that, then that will emits the light. That will emits the light means converts the electrical energy into light. Electrical energy into light. Next one is a photovoltaic devices like solar cell, photovoltaic solar cell. That is which converts the optical radiation into light. Means whenever the sunlight is incident on the solar plates, then that can be converted into the light, or some of the electricity it can be stored as electricity, and it gives the solar cells means photovoltaic device, so which sparkles will come from that and it illuminates. So that's why that type of materials are photovoltaic devices. In this case, first of all, we are going to optoelectronic junction devices. We are going to discuss about a photodiode. Photodiode, a PN junction diode made photosensitive materials like photosensitive. PN junction diode is made up with the photosensitive semiconductor materials. Then that is called as a photodiode. Means whenever the light is incident on that, then it can be reverse biased. So that's why whenever the light is incident on that material, then that can be absorbed. That will be absorbed. Due to that one, the conduction is possible in the PN junction diode. Means here that this is the PN junction diode, and whenever it is heavily doped, means whenever the light ray is incident on this material, this is the photosensitive material. Here between this photosensitive material will be occurs whenever the photosensitive substances means light is incident on that. It can be connected in reverse bias. This P type of metal connected to negative charge of negative terminal of the battery, and N type of a material is connected to the positive terminal of the battery, and it is connected in reverse bias. Whenever it is connected in reverse bias, whenever the light ray is incident on that, when the conduction will be increases, means whenever the light rays intensity is more, then the conduction in the PN junction diode is also more. Due to that, it will absorb the more amount of light ray. So that's why here the wavelength of light is incident on the body, then that can break the valency bond, and conduction will be possible because of whenever the valency band is breaks, and another new number of electron hole pair will be created. Already we discussed in the bond, means the PN junction diode. Already we discussed in the PN junction diode, whenever the suitable of frequency is incident on that, then the valency bond breaks and a new of holes and electron pair can be created. Due to that one, the conduction will be more and more in the at the junction. So wherever the no more in that, here the photodiode which function controlled by the light falling on it. A diode which can be controlled by the when the light is falling on that. If the more intensity of light is falling on that, then more conductivity will be PN junction diode. So that's why you can say that if the conductivity of PN junction photodiode increases with the increase in intensity of light falling on it. Whenever the more light is incident on this material, then more conductivity will be happen in the PN junction diode. So this will be the symbol of a photodiode. Means a light ray is like in inward direction. The direction will be in inward direction. If in case of the direction will be in opposite direction, if the direction is like this, then that will be the symbol for the LED. So this is about the symbol of a photodiode. The arrows must be means light is incident on the diode. So here is also light is incident on the diode. So here the PN junction diode, which is made up of with the photosensitive semiconductor materials, then that will be the photodiode. It is connected in reverse bias, so it is can be controlled by the when the light falling the light incident on it. So that's why suppose the light of wavelength lambda is sufficient to break the valency band. Means the wavelength of lambda light is incident on this, then in this case of PN junction diode, the valency bond can be breaks. So when the light falls on the junction, then new hole pair can be created, new hole electron pair can be created, so that the conduction will be more and more in such a diode connected in the circuit. The current may be controlled by the instanting light. If the instant light is increases, then the conductivity in the photodiode is also increases. So this is about here the graph we can say that it is the potential and this is the current in microammeters. Microamps, that will be the microamps with the here the ammeter we can measure the how much the current is flowing through the circuit. If the intensity of radiation is moving more, then the voltage is also more, intensity of current is also more, like this. Here conductivity of PN junction diode for PN junction photodiode increases, means whenever the more light incident on this, then more potential intensity of potential will be increases like that I5 greater than I4 greater than I3 greater than I2 greater than I1. If the more light is incident on this material, then there will be more conductivity will be happen, means more current will be happen. So this is about the one of the optoelectronic junction devices, in that case of a photodiode. Next we are going to discuss about that the applications, means what are the applications of photodiode, means what are the photodiodes in which the devices the photodiodes can be used, means here the normally we can say that the clock radios and as well as camera light meters, which is projected in case of like we can see the like the umbrella type of materials. In that case of photodiodes can be illuminated. When the light is incident on that, then that will be absorbed, some more intensity conductivity will be happen. So camera light meters and also clock radios in the receivers of remote controls also. Whenever the remote control will happen, then receivers, in the receivers of the remote controls also the photodiode can be useful in TVs or either whatever the electronic devices which is using by the remote controls, like that. Then also to measure the extremely low light intensities. Low light intensities that can be measured by using this photodiode. And also consumer items like camera light meters and clock radios and receivers of the remote controls in VCRs and televisions, and as well as to measure the low light intensities extremely in avalanche photodiodes. Avalanche, we know that avalanche breakdown. In the case of avalanche photodiodes are photo multiple tubes are using in spectroscopy and astronomy, to see about the astronomy, and also night vision equipments. Without glare we can see the everything in the night also. So that's why the type of materials which is used for the night vision equipments also the photodiodes can be useful. And also large range finding, laser range finding, large amount of laser range finding also in this case of photodiodes can be used. And also pin diode. Pin diode means here pin diodes are much faster and sensitive more than the PN junction diode. Pin diodes are faster and sensitive materials that they are used for the communication purpose. That pin means positive intrinsic negative diode. Positive intrinsic negative diode means a heavily neutral doped, a large neutrally doped intrinsic semiconductor is sandwiched. A large neutrally doped intrinsic semiconductor is sandwiched with the p doped and n doped materials. P doped and n doped diodes, then that can be the pin means a positive intrinsic negative diode can be formed. Then the diodes are used in much faster and more sensitive also. These diodes can be used in a communication purpose. So these are the applications of photodiode that can be used. The photodiodes can be used in this purpose, like astronomy, like camera light meters and radios, clock radios, and as well as spectroscopy. And pin diodes are used for the communication purpose. They are the more efficient, more faster and more sensitive also. So these are the applications of photo light emitting diode. This is also one of the application which is used to PN junction diode in this. When the PN junction diode is heavily doped in forward bias, PN junction diode is heavily doped in forward bias, then the P type of materials, whenever this emits the light, that is a light emitting diode. That is light emitting diode. Light emitting diode is a photoelectronic device which converts electrical energy into light energy. Electrical energy into light energy. Light emitting diode is a photoelectronic device which converts electrical energy into light energy, and it is a heavily doped PN junction diode in forward bias, emits a spontaneous radiation. Nowadays we are using LED bulbs mostly, and also we can see that if we see the remote, TV remote and water out of the remote, at the inside we can see some of the sparkle radiation, some of the light is blinking whenever we press the button, means that light is a LED bulb, means that emits different colors also, like red, orange, yellow, green, blue. Several type of lights can be emitted by the light emitting diode. That light emitting diode will emit different colors of light. That is radiation. Whenever the PN junction diode is heavily doped in forward bias, then it emits a spontaneous radiation. So that is LED. This is the symbol of LED, means this is a P type of material and this one is a type of material. Whenever these are heavily doped, the emission radiation is emitted in outward direction. If in case of the arrows is inward direction, that will be photodiode, and arrows are in upward direction, it will be the symbol for LED, light emitting diode. Light emitting diode. This is the circuit, whatever the light is there, we are seeing that this is a P type of a material and this one is the N type of a material, and light emits from this. Whenever we connected the battery, it is forwardly biased, means P type of a semiconductor is connected to the positive terminal of the battery, and negative terminal of the battery is connected to the N type of a material, means it's a forward biased. Whenever this forwardly biased, in this P type of a material, the majority charge carriers are holes, and in the N type of material, majority charge carriers are electrons, and minority charge carriers are electrons, and minority charge carriers are holes. So here it is that when it is PN junction diode, heavily doped PN junction diode is forwardly biased, then the electrons will move towards the junction. Junction means from P side, N side to the P side, electrons moves from N side to the P side, and holes move from P side to the N side. P side to the N side means conduction will be happens. So through the junction, then the depletion layer width will be decreases. As a result, these minority charge carriers rapidly increases at the junction. At the junction, the minority charge carriers are in this place will increase rapidly. Then if we can say when there is no any bias, means there is no any bias at the junction, no bias at the junction, then here the minority charge carriers will recombine with the majority charge carriers. Once again, when the PN junction diode is forwardly biased, then the holes move from P side to the N side and electrons move from N side to the P side, then conduction will happen. At the junction, the minority charge carriers are rapidly increases. Wherever there is no bias at the junction, those minority charge carriers will recombine with the majority charge carriers. So due to that recombination, due to that whole electrons are recombined with the majority charge carriers, then at the junction the energy given out from the diode in the form of heat and light, so that here we can say that whenever the forward current is increased, means whenever it is forward biased, forward current increases. Whenever the forward current increases, then the intensity of light emitting diode is also increases, and further increment, if in case of the forward current is small, then the intensity of a light emitting diode is also small. If the forward current increases, then intensity of a light emitting diode also increases and reach to the maximum value. So that here we said that energy is emitted from this. Wherever the forwardly biased, the minority charge carriers recombine with the majority charge carriers, and due to that the radiation will emit from this. So that's from the diode. So that here we can say that the radiation in the form of heat and light, it can be emitted. Those are called as photons. Photons in the form of heat and light, they are emitted from the light emitting diode, that is photons. So that photons have the energy with equal to the bandwidth between the band. So here the photons are emitted from the light emitting this diode. So here it is that whether the forward current is small, then the intensity of diode is also small. And as well as we said that different colors can be emitted from that. Their capacity will be up to 3 electron volts to 1.8 electron volts. It is used for, means the light emitting diodes are made with the gallium arsenide or phosphide, with making with their gallium arsenide is used for making the light emitting diodes. And also here it is that we can say that here whenever the light is emitting from this, we said that the forward current is small, then the intensity is also small. If the forward current is increased, then it reaches to the maximum value. Intensity of the light emitting display also increases and reaches to the maximum value. Beyond that maximum value of the intensity of light, further increment of the forward current, the intensity of light emitting diode decreases. So that's why we can say that the efficiency is maximum for LED. So nowadays, severally we are using the LED bulbs, right? So here is that the efficiency is a maximum of a light emitting diode. This can be displayed. This can be available in nowadays in a wide range of colors. Means like red, green, yellow, orange, blue colors are for the commercial purpose. These are all made with the gallium arsenide and phosphide for the different colors. There is a different combination for the different colors, intensity due to the intensity of the different colors we can get in for the commercial purpose. This is about LED. LED means light emitting diode. Light means, once again, light emitting diode is a photoelectronic device which converts electrical energy into light energy. A heavily doped PN junction diode which emits the spontaneous radiation, whenever they are doped in forward bias. So this is the symbol of a light emitting diode. Then this is the working construction circuit for the light emitting diode. This is the P type of a material and N type of a material. This P side is connected to the positive terminal of the battery and N side is connected to the negative terminal of the battery. So that whenever it is connected, the electrons are moved from the N side to the P side and holes moves from P side to the N side. So that the width between the both were biased at the junction depletion layer width will be decreases, so conduction will be happen. Due to the minority charge carriers will form, increases rapidly at the junction, when there is no bias at the junction, then the minority charge carriers are recombined with the majority charge carriers. And emits the radiation in the form of heat and light. Those are called photons. so that the forward current will be passing through the circuit. If the forward current is small, then the intensity of light emitting diode is also small. If light emitting diode intensity is small, then the forward current increased, then the light emitting diode also intensity also increased and reaches to the maximum value. Further increment of the forward current, then there is no increment in the intensity of light emitting diode, in case the light emitting diode intensity will be decreases. So that's why its efficiency is maximum. So this is about light emitting diode. Nowadays commercial purpose, number of several type of colors we can get at in the market. Applications and advantages of LED. Here the applications are where the LED bulbs can be used. LEDs, light emitting diodes can be used. Light emitting diodes can be widely used. Large number of applications are there. In nowadays, in every electronic gadgets having that LED, like mobile phones and digital watches and whatever the displays is there, TVs, televisions. Total number of image sensing sensors also using in the LED bulbs, also using in image sensing sensors. So right here, burglar alarms in the hospitals and in the banks and in the some of the places, burglar alarm systems. In this burglar alarm systems, LEDs can be used. And nowadays also, if we went for the supermarket, then if we some of the groceries we have taken, they are scanning that barcode, with the LED light. So these are the light emitting diode. So like that also, that is for the reading purpose and as well as for the scanning purpose, and as well as here also in burglar alarm systems also we can use the LEDs, and also in calculator and digital watches. Nowadays we are using the different type of watches for fitness purpose also, for the to know the times also, everything. To know the display the numbers, numerical numbers, to display that one, the LED bulbs are small type of LEDs are using light emitting diodes are using in calculators, and as well as here the digital watches, LED used for the number display, and also in the field optical communication. Field optical communication means in optical fiber communications which is suitable for the high radiance gallium arsenic diode, which is matched up with the optical, where the for the suitable matched for the optical fiber, their light emitting displays also we are using for the indication purpose also in optical communication. And in computers like optical mouses, nowadays optical mouses without wire we are using the optical mouses, and also keyboards, and also same has for the memory purpose also in computers we are using it. To display this, there is also some of the mobile phones, and in nowadays mobile phones, video games, and at the same time video displays, the image sensing circuits, in the purpose of image sensing circuits in televisions, mobile phones, and as well as video displays, total everything the LEDs can be wide rangely using. In traffic light also, here the traffic light green, yellow means orange, red. In that also small LED bulbs can be used to display for illuminate traffic lights, and for the remote control also. In the remote control also we have the sensor bulb is there, that bulb is also LED bulb, that means light emitting diode bulb, which can be used to transfer the data. Also for the electronic, to transfer the data to electronic gadgets, whatever the gadgets are we are using. If we change the number in the remote, then in the television also, in the ACs also, in the electronic device, that can be changes for whatever we changed that one, it can be operated by the LED to transferring the data to control the transmit the information to the electronic gadgets. These are the normal few of the applications which are LEDs are used. And the advantages of LED. What is the advantages of LED? LED advantages means these LED bulbs are very cheap and low cost for the everyone, and also it can be easily handled and also it having less power which is used for the LED. To use the LED bulb, the less power it consumes, and also it is operational also low operational voltage. So that's why by using the LED we can reduce the cost of electricity also, and also less power and low operational voltage, and fast action and requires no warm up. In tube light, if we put on the tube light at home, it will take for a while to come into the display, for it will get a warm up first of all. Before, if we use the LED, it does not require no requirement of any warm up, and fast action will be there, and also it is cheap and easy to handle, and as well as use it for variety. Now we are use it for variety means like burglar alarms in mobile phones, in watches, calculators. In nowadays wide rangely we are using the LEDs. This is about LED light. Solar cell means when the light is incident on the device, a device which is used to convert the energy, means convert solar energy, which is the light we can get from the sun, that solar energy into the electrical energy. That means here the basically a PN junction diode generates EMF when solar is incident on that. Here we are taking this 3 plates which is having that N type of P type of a P side of a material, which wafer is above this wafer of the N type of a material, and below the P type of a material the black contact will be there. So when the light is incident on the top of the N plate, these metallized finger electrode is placed, which occupies the place 1.5% of the place is there. When the light is incident on that, then here the photovoltaic effect will be happen. What is meant by the photovoltaic effect? Photovoltaic effect means when the suitable frequency of light incident on the open circuited solar cell, then an EMF is produced across its terminals. When the solar light is incident on the open circuited solar cell, the EMF is produced across its terminals. So that EMF is called as a photovoltaic EMF. The EMF is called as a photovoltaic EMF, and as well as here the effect which is happen during the process. The process is going on that, the effect is called as a photovoltaic effect. Once again, solar cell is converts the which converts the solar energy into electrical energy. A PN junction diode produces the EMF when the solar energy is incident fall on it. So here is that this is also like a photodiode, is a photovoltaic effect will be happen when the light or sunlight is incident on the solar cell, then EMF is generated. That EMF is called as a photovoltaic EMF, and the effect during the process to produce the EMF is called as a photovoltaic effect. We can say that here the construction, we can see that what is the how to solve this solar cell can be constructed by taking this P side of wafer about 300 micrometer thick there, the thin layer which can be taken, and over this N type of a material, means the N side of ground is on one side by diffusion process, for the diffusion process. So other side of a P side coated with the metal, P side coated with the metal. On the top of the N silicon layer, metal finger electrode, this will be the metal finger electrodes is deposited, acts as a front contact. Front contact means which is taken the solar energy and it will send to this nearby the downward plates. So thus here this total metal plates electrode will occupies the 1.5% of the cell area, total cell area 1.5% of the cell area. When light falls on it, EMF is generated. EMF is generated in 3 steps, means by generation, separation and collection. These 3 steps are done by this. Whenever the light is incident on the solar cell, then so according to this, the solar from the solar cell, the light is collected, generated, the EMF is generated and separated their holes and electrons, and they are collected from the electrons and protons, which is made by the positive and negative terminals. So here it is that what is the process which is going on. First of all, construction means when all p side wafer about 300 micrometer taken over, 300 micrometer taken over a thin layer, and of n side is grown on the one side by diffusion, and means p side taken one side of the another, and another n side of this taken over the grown over to fix the metallized electrode which can be 1.5% of the place of the total cell area is occupied, and that is acts as a front contact when the light is incident on this front contact, so that when the light falls on it, this produces an EMF generated in 3 steps. Those are generation, separation, and collection. So here it is, first of all, what is generation? Means when the light is incident on the solar cell, the EMF is generated. Means when light falls at the junction, electron hole pair is formed at the junction. That means generation. Means when the light falls on the junction of PN junction which has taken that, then the circuit will be like this. When the light is incident on the, this is P type, this is only L type, and we can get the circuit like this. So this is load resistance we can get, the current will be photo current we can say. So here is that, then HV means H nu means the photons are incident on the junction. At the junction whole electron pair can be generated. So near the junction, that is about generation. The next one is separation. Separation means here due to the electric field of depletion region, the photo generated electrons and holes, the photo generated electron or holes will move opposite directions, electrons swept towards the n side, and holes moves towards the p side. Means due to the electric field of depletion region, photo generated electrons and holes, when the light is incident on that, then electron holes are generated at the junction. That at the junction the photo generated electron and holes are moves in a opposite direction. They will move into opposite direction, and the electrons will move towards the n side, and holes can be taken to the holes move to the p side of a junction, p side of a material in the solar cell. Then next, collection. When light is incident on the PN junction and hole and electron pair is generated, that is called as generation. Whenever the generation due to the electric field of depletion region, the holes and electrons, photo generated electron and holes move in opposite direction, the total holes towards the p side, and holes electrons will move towards the n side. Then what is the collection? How do they collection? Collection means if no external load is connected, if there is no any external connected to this, the electrons reaching the n side and the holes reach to the p side in front contact. Means whenever in front contact, means whenever this we have taken this 3 times here n, p, this is the black metal which is connected. So here whenever the light falls on it on the front contact, this is the front contact. So whenever this front contact, the total electrons moves inside and holes move to the pure p side. Then from the front contact, and holes reach the p side, and total the electrons reach the front side contact, the n side, and total holes reach the back contact of p side. Thus p becomes positive and n becomes negative, giving the rise to the photo voltage. By giving this, when that there is no any external load is connected to this, then the total holes moves towards the collected by the p type of material here, then for the back contact, and electrons moves for the front contact, so that this total p becomes positive and n becomes negative, giving rise to the photo voltage. This is about a solar cell. This is about a solar cell, means whenever it is contacted, then the photo current is a photo current IL moving in this direction, then at the same time the load current we can take the output voltage, so that here we can take the total positive taken this side and negative taken this side. Due to that one, we can use widely, solar cell are using widely nowadays. So to reduce this, some of the cost of electricity, and also for the different purpose, which can be in cooking food also we can use the solar electrical, and as a pumping water, in pumping water and cooking food, the use of the solar cell. Then to charge storage batteries in daytime, means whenever we put the solar cell in our top of the home, then we can get that in the daytime due to the sunlight, due to the solar cell, that batteries, means storage batteries can be recharged, and whenever we lost the power in our home, then we can use we can use that storage batteries to produce the electricity to continue. So in calculators, we know nowadays we are using, and wrist watches and light meters in photography, and as well as in artificial satellite and space vehicles. We can't produce the electricity, continuous electricity, whenever the artificial satellites sent into the moon or whatever in orbitals. So the solar plates, means solar cell can be used for the photo electronic devices, of the photo electronic devices which is used in the artificial satellites, the power generated by the solar cell, and also in a space vehicle also by the solar cell we can produce the electricity to continue the photo electronic devices which are used in the artificial satellites and space vehicles, and as well as produce electric powers in remote, which we cannot supply the electricity through the lines in remote villages, which is far away from this, for the remote villages we can produce the electricity by the solar cell, and also remote radio telephones and the traffic signals also. For the traffic signals also we can produce the electricity. In the daytime, that light will be incident on that solar plates, and storage in the storage batteries that can be stored, and whenever at night time we lost that, then it can be used for the traffic signals. Transistor. In earlier videos we discussed about that the p type of materials and n type of materials, and as well as the p-n junction diode and the applications of p-n junction diode whenever it is connected in forward bias and connected in reverse bias. Then LED, solar cell, photodiode, about that we have discussed. Now we are going to discuss about when a p type of a crystal, means the positive holes consist by the p type of a semiconductor material. In that p type of a crystal is sandwiched with the n type of a two crystals, or n type of a crystal is sandwiched with two p type of a crystals, then a transistor is formed. Transistor, which is a device which can be done with here the oscillation, is the amplification and rectification, as well as it can do much more. So in that case, first of all, what is transistor? Transistor means it's a combination of two words, that is transfer and resistor. Means here we can take that a transistor consists of a p type of a crystal is sandwiched between the two n type of crystals, or n type of a crystal is sandwiched between the two p type of a crystals, then the transistors, two type of a transistors can be formed. Those are here the transistors are two types, that is PNP and NPN. PNP and NPN are the two type of a transistors. Here the PNP means this is the positive, is considered as a emitter, and in this case of this one is base and this one is a collector, and in case of NPN is also there, this is considered as emitter and this one is base and this one is a collector. This is the NPN transistor. Means here the N type of a crystal, N type crystal is sandwiched with the two P type of crystals, then the PNP transistor can be formed. And as well as here the P type of a crystal is sandwiched with two N type of a crystals, then the NPN transistor can be formed. N transistor can do amplification, oscillation, and as well as rectification also. So that's why we can say that the transistor much more can do in the electronic device, wide rangely using the transistors. So here it is that the symbols of the two transistors, so that is PNP transistor and NPN transistor, symbols of both. These are the PNP transistor. Listen carefully, this is the most important for the intermediate public examination for the 2 marks. He asked for the draw the symbols of PNP and NPN transistors. Then these are all this. Here this is the symbol of a PNP transistor, and as well as this one is the NPN transistor. In this case of the arrow will gives the difference between the PNP and NPN, because of we know that always charge flows from the positive to the negative, right? So from plus to the minus. Here the P consists of, we know that P consists of holes, majority charge carriers are holes, and N consists of majority charge carriers are electrons. Means always current flows from the positive terminal to the negative terminal. Here is also always the holes moves from the P to N. So that's why here PNP means this is the P terminal and this is the N terminal and this one is the P terminal. Here is that whenever the current flows from emitter to always emitter to means this P type to the N type. So that's why arrow is directed towards the emitter to base. Emitter to base, that P side to the N side terminal. Then this will be the PNP transistor symbol. Symbol of PNP transistor. Here is the direction will shows the flow of charges. Flow of charges. Either in case of NPN transistor, here we know that this is N terminal, this is P terminal and this is N terminal. Then current flows from the P side to the N side. Here we can say that from P to N, the majority charge carriers in N is electrons, so that's why these holes occupies the electrons always. So here is also holes occupies the electrons. So that's why here from P side to the N side, the arrow will gives the from base to the emitter, then the arrow will gives the difference between the NPN PNP transistor, that is the direction of flow of majority charge carriers, which is consist of it is heavily doped materials is consist of will decide the direction of charge. So that's why here the heavily doped emitter is having that P type of a semiconductor, and so that's why here from the holes to the electrons. Here is also emitter is having the N type of it is connected majority charge carriers in the other electrons. So that's why the flow from the P to N, always P to N be the direction. So that's why here PNP and NPN. The arrow must be denoted between the emitter to the base. Why? Because of here let's see the transistor can does a rectification, amplification, oscillation also. We know that we already discussed about that. And also transistor is a combination of two words, that is a resistor and a transfer and a resistor. So that's why the transfer from emitter, these are the 3 parts consist of transistor consist of 3 parts. Those are emitter, base, collector. Emitter, base, collector are the 3 parts consist by the transistor. Here is that first of all the emitter. What is meant by the emitter? This one is the considered it's a NPN transistor. This is a emitter. The terminal is a emitter. In this case, it's a heavily doped crystal which supplies the majority charge carriers. Means in this case of this is a majority. This is highly doped crystal, either N type of a crystal or P type of a crystal, whatever it is. In case of the emitter is a whatever the emitter. This is emitter. This is base, this is collector. So here it is that the emitter is a heavily doped. This is heavily doped. So that's why this gives the majority charge carriers. Means the main role played by the majority charge carriers to the conduction. So that's why emitter is emits the majority charge carriers, means gives the majority charge carriers to the circuit whenever it is connected in the circuit, and is also it's a thinner than the collector. It is thinner than the collector and thicker than the base, means it is having the middle in a size. So that's why here almost all for the commercial for our convenience to show the commercially to show our for our convenience, the collector emitter can be drawn with the same size. So but it is thinner than collector. The emitter is thinner than collector and thicker than base. So here it is that is emitter is a heavily doped crystal which supplies the majority charge carriers either in PNP or NPN transistors. Emitter is a heavily doped crystal which supplies the majority charge carriers, and it is thinner than collector and thicker than base. Thinner than collector and thicker than base. In the circuits, the charges supplied by the emitter only. The next one, base. It is a lightly doped crystal. Base is a lightly doped crystal which is always it's a very thin material, thin size. It passes the most of the emitter injected charges, means whenever the charges are injected to the from the emitter to the base, the total emitted charge carriers from the emitter can be passed to the collector. Most of the charges, whatever the most of the majority charge carriers passes towards the collector. Means when the emitter emits the majority charge carriers and send it to the base, then that base will passes the total majority carriers into the collector. Total majority charge carriers sent to the collector. Most of the charge carriers are sent by the base to the collector. That is the function of a base. That is only base will transfer the emitter, means which emits the majority charge carriers in the circuit. It is sent to towards the junction. This is the junction and is sent to the base, and base which passes the majority charge carriers which is emitted by the emitter into the collector, means transfer, that will transfer the collector. That is the main role of a base. And one more thing is, last one is a collector. It is a normally means moderately doped crystal, thicker than this is the most thicker one, because of most of this time more than the thick, this one is the thicker one. So it is the function to remove the charges. At the junction, means whatever the charges lied at the junction, means collector base junction is there. Here the junction between the base and collector, means whenever this emitter, base, collector at the junction, they remove the charges from its junction with the base, means it will transfer the electrons and it will emit the electron, it will emit the charges, and as well as the base will transfer the charges, and this collector will remove the charges. So that's why whenever it is removes the collector due to the magnetic charge carriers pass at the junction, it will combine with the charge carriers, and means electron hole pair can be formed, so that the collector current will be done. So that's why here the collector current most of the here will considered as a emitter current, due to the charge carriers are supplied, majority charge carriers supplied by the emitter. So that's why here the collector current will pass us through the circuit. So here it is about the primary information about the transistor. First of all, transistor means it's a sandwichly biased one type of a crystal with the another two type of crystals sandwichly, then that is called as transistor. Means either then a P type of a crystal is sandwiched between the N type of a crystals, or N type of a crystal is sandwiched between the P type of a crystals is considered as a transistor. Either PNP or NPN transistor. There are two type of transistors are there. In this case of PNP and NPN transistor. In this case, the first one is considered as a emitter, which is heavily doped, but it is thinner than collector and thicker than base. which is medium. So in the case of that second one is these are the symbols of transistors, that is PNP and NPN. The arrow will gives the direction will gives the difference between the PNP and NPN. Always flows from the charges flows from the P to N. So that's why here PNP. So that's why P to N. Only the arrow should put between the emitter and base only, because of emitter emits the majority charge carriers and base will take that values and take the charges and transfer it into the collector. So that's why here emitter always positive to negative. Emitter means here P type from always direction shows from P side to N side. Here is also P side to N side, because of we know that emitter will emit if the direction is in this case of electrons will always attract the holes. So that's why here the N means the majority charge carriers are electrons. So that's why from the positive side to the negative side always charge will flow. So that's why here taken that is in along the P to N direction, the direction will be shown. This is the NPN PNP diode PNP transistor symbols. In this case of the transistor consists of three parts, that is they are the emitter, base, collector. In the case of emitter is a heavily doped crystal. It is the first one is this a heavily doped crystal, and which is considered a emitter and which emits the majority charge carriers, which is injected or supplies the majority charge carriers into the circuit. Then it is thinner than a collector and thicker than a base. So, but in case of for our convenience, we will write that collector and emitter in the same size. The base will be in a small size. So next one is a base. It is a lightly doped, which is passes the charges which is emitted from the emitter. So that's why he passes to the collector. And the collector it is the moderately doped crystal and thickest one in the transistor, and as well as its function to remove the charges at the base collector junction. And this is the base collector junction. It removes the base collector junction. It removes the charges in the base collector junction. This is about the primary information about the transistor. So in earlier video we discussed about the transistor and the types of the transistor. Now we are going to discuss about the working of a transistor, either PNP or NPN. Means here first of all we are going to see that what is the PNP transistor, working of a PNP transistor. Already we know that. From that, here in PNP transistor circuit consists of emitter, base, collector. In this case the holes are the majority charge carriers which can in this transistor the holes are the majority charge carriers in the resistor, in the transistor. So here it is that this is emitter, base, collector. Consider this PNP transistor circuit is biased, the common biased by the collector, and emitter is commonly biased at the base, and both are commonly biased, and that there are two loops are there, and this one is the one loop and this one is the another loop. Means here emitter base loop here once again, and base collector base is there, base loop is there. So from this, here that emitter base is given a small forward bias. Means here we know that this is PNP. This emitter is a P type of a material, and here N is a N negative terminal, means N type of a material. So that's whenever the P type of a material is connected to the positive terminal of the battery and N type of a material is connected to the negative terminal of a battery, it is a forwardly biased. The small forward bias given to this emitter base junction, emitter base region, given a small forward bias that can be emitter can emit the electrons, holes from the P type of material, and base can transfer that into the collector. So here it is that a small forward bias connected in the emitter base region, and if we come for the second loop, that is the base collector region. In the base collector region is given the high reverse bias. High reverse bias means the negative terminal of N type of a material connected to the positive terminal of a battery, and negative terminal given to the P type of a material. Means it is reversely biased. Whenever it is reversely biased, then the circuit is some of the circuit means emitter base junction given a forwardly biased, a small forward biased, and a base collector junction given the heavy large reverse bias. In this case of when forward bias, in this forward bias we know the conduction will be possible. When forward bias, the emitter based region, in the emitter base region holes moves from the emitter to the base. Holes moves from the emitter to the base. Most of the holes, up to 98% of the holes moves from the emitter to base, and remaining percent means 2% of the holes will combine with the electrons, which is at n type of a material. Means whenever they combine, due to that combining these 2% of less amount of holes are combined with the electrons in the base, so that base current flows through the circuit. Means here the base current will be possible due to that whenever the emitter base region is forwardly biased, most of the holes will move from the base and enter into collector region. Means whenever this is forwardly biased, once again whenever the emitter base junction is forwardly biased, this emitter will emit the holes and enter into the base. Most of the 98% of the holes will moves into the collector region, and remaining 2%, up to nearby 2 to 10% of this 2% remaining small amount of percentage of holes will combine with the electrons, which is at in n type of a material. So that here is that due to that recombination of the whole electron, the current will be possible, that is base current is flows in the circuit, that is called a small current, that base current, that is called IB, that is IB, and the holes enter into the collector region and combine with the electrons, which is provided by the battery negative terminal. Means the 98% of the holes is emitted from the total holes are emitted from the emitter and reach to the base, and that base is 98% of the holes are transferred to the collector. In this transferred holes are combined with the electrons, which is provided by the, because of it is connected to the negative terminal, the holes are positive and the terminal gives the negative electrons. So that's why here the amount of 98% of the total amount of current will comes from the negative terminal. Whenever it gives the electrons, then the holes are combined at the due to the connection of the reverse bias. This is attracted by this. This is holes are combined with the electrons at the collector region. The holes enter into the collector region and combine with the electrons coming from the negative terminal, that is the collector current flows, that is IC, means collector current. This causes collector current. Both this collector current as base current constitutes the total emitter current, because of in external circuit the majority charge carriers, in the transistor the holes are the charge carriers, and in external circuits the electrons are the charge carriers. So that's why here, due to that, here both collector current and base current constitutes together the emitter current will be happen. That is IE is equal to IB plus IC. So base current nearly in the emitter current, base current is nearly up to 2 to 10%, and collector current is 90 to 98% will be constituted in the total emitter current. Means in the emitter current, the less amount of current will be base current and most of the large amount of current will be collector current. Once again, the working of a PNP transistor is by connecting this PNP transistor to the batteries in such a way with the common base bias, then here the emitter base, E means emitter, B means base, C means collector. So emitter base junction connected, emitter base junction means our emitter base region is connected with a small forward bias, and base collector region is connected for a large reverse bias. When we connected the forward bias, due to this forward bias, the emitter emits the holes, large number of holes into the base, And a base, from the base holes 98 large and most of the holes will transfer to the collector by the base, and remaining small amount of holes will combine with the electrons in the base, so that that causes the base current, that causes the base current. And whenever the holes are reached to the collector and combine with the electrons which is coming from the negative terminal of the battery Vc, negative terminal of the battery Vc. Here once again, whenever in the base current, when the base current, in the base current the holes are entered, some of the amounts, some of the holes will combine with the electrons, then the electrons will leave the negative terminal, because of here the negative terminal is there now. So that's why here in this case of electrons, whenever we combine with the holes, they leave the negative terminal and combine with the electrons, and due to that this causes the base current. And whenever the maximum amount of holes are entered into the collector, then they combine with the electrons which is coming from the negative terminal of the battery Vc. So that causes the collector current IC, that causes a collector current IC. So in that case the collector current and base current both together constitute the emitter current, both constitute the emitter current. So in that emitter current, the base current is 2 to up to 2 to 10%, means less amount of base current will be constituted in the emitter current, and most of the current will be collector current, that is up to 90 to 98% for the emitter current. This is about working of a PNP transistor. We are discussing about working of a PNP transistor. Now we are going to know about NPN transistor, the second type of a transistor, which is NPN transistor. Already we discussed about it. NPN means the P type of a crystal is sandwiched with the another N type of P type of a N type of a crystals, two crystals, then that is called as NPN transistor will be formed. And in case of NPN transistor, this is a N type of a material and P type of a material is sandwiched, and this is also another N type of a material, and the first one is lightly doped, and here whereas emitter is a heavily doped material and base is a moderate lightly doped, and this one is a moderately doped. So that's why here it is having the more, these two are having the electrons are the majority charge carriers in the circuit in these crystals, and as well as NPN transistor connected in the same bias as earlier we discussed about the PNP transistor, same as here also. The emitter base junction is forwardly biased, means here NPN transistor is there. In case of this one is N and this one is P type of a crystal. So here it is that the negative terminal of a battery VE is connected to the negative terminal of the N type of a crystal at the emitter, and at the base the positive terminal of the battery is connected to the P crystal, it means base. So this is a lightly forward bias, that is with the VE. This is the VE is the battery, VE is the battery, with the battery small forward bias is connected, and the base collector junction is connected reverse bias. This is P type of a crystal, so that's why the base, this is the negative terminal, this second loop, this one, and this is the N type of a material, means N crystal, so that's why here this is connected to the positive terminal, means reversely connected, so that's why it is a large reverse bias, largely reverse bias. The operation is also same as PNP transistor. Here emitter emits the electrons which sent to the base. Emitter emits the electrons due to the forward bias, this one is a negative, and this is also N type of emitter, so due to the repulsion the total electrons move towards the base emitter junction and jump from the junction and enter into the base, and when the base is sent, the base as well as this one, the most of them sent to the collector, the remaining electrons are combined with the holes which is provided by the positive terminal of the battery V, which is connected V. So that here whenever these are holes, electrons are combined with the holes in the base, then the bond breaks in base region and produces whole electron pairs. This constitutes that is IB. IB means base current. Once emitter emitted the electrons and enter into the base, when 98% up to most of the electrons are sent to the collector, the remaining percentage of collectors are combined with the holes. Whenever they combine with the holes, a bond breaks in the base region. That constitutes that base current. Is in the direction, means emitter current follows like this, and base current is in this. So that's why the current will flows in the circuit. Base current, the small amount of base current will be flows in the circuit. The electron captured by the positive terminal. So that here the electron, whenever electron captured by the positive terminal of the battery, that VE, and sent towards the emitter region. Emitter region. So that this causes the sum of the base current. Once again, when emitter in forward bias, emitter base junction, the electrons move towards the base. Most of them sent to the collector. Very few of them are combined with the holes, and whenever they combine, the bond breaks at the base region, and the electrons are acquired by the battery, positive terminal of the battery, and sent towards the emitter, region. This causes small base current in the circuit. So when the remaining most of the electrons are entering into the collector, this collector alternatively positive terminal of VC acquired by this entered into the positive terminal of the battery, it will be attracted by these are the reactive charged particles, and this one is the positive terminal. So that's why the entered electrons will attracted by the positive terminal of the battery VC, so that the collector current constitute. This causes the collector current IC. So that this base current and collector current together constitutes the emitter current, same as earlier we discussed in the PNP transistor also. So that the collector current and base current both constitutes together the emitter current. The base current is less 2 to 10%, which depends on the doping level. And also here collector current will be up to 90 to 98%. This is collector current, and base current will be 2 to 10%. So that here the emitter current will be base current plus collector current. This will be the total emitter current, together the collector current and base current. Once again, in that NPN transistor, the emitter base junction is connected in a small forward bias with battery V, and base collector junction is large reversely biased with battery VC. Due to the forward bias, the electrons are emitted by the emitter and sent to the base. In that emitted electrons, most of the electrons are sent to the collector, and some of the electrons will combine with the holes. Whenever they combine with the holes, the bond breaks at the region and forms whole electron pair. So that due to that pair, the positive terminal attracts the electron and sent towards the emitter region. The positive electrons are attracted by some of the electrons which are stayed in base will attracted by the positive terminal of the battery VE and sent to the emitter region. So that causes base current, small base current in the emitter base region circuit. So when the most of the electrons are sent to the collector, the electrons are attracted by the positive terminal of the battery VC. So that causes the collector current in the circuit. So that IC, collector current and base current together constitutes the emitter current. So that emitter current nearby 2 to the base current is nearly 2 to 10% of the emitter current depending upon the doping level, and the collector current remains 90 to 98%. Here the electrons are the majority charge carriers, the electrons are the charge carriers in the transistor as well as in the external circuit also. Because of the electrons only in external circuits, so in always due to the electrons only the current will be passes through the circuit in external circuit. So that's why in the PNP transistor or NPN transistor in external circuits the charge carriers are always electrons, but the holes are charge carriers in the transistor when in the PNP transistor, because of in PNP transistor holes are the majority charge carriers. So that's why in the transistor, with the transistor only the charge carriers in the transistor is holes in PNP transistor. In NPN transistor, electrons are majority charge carriers, and in the external circuits of PNP and NPN transistor both the electrons are charge carriers. After discussing about the transistors and types of transistors, they are the PNP and NPN transistor. We discussed about the working of a PNP and NPN transistor also. Then if we want to connect the transistor in the circuit, we just need 4 terminals for that connection, two connections for the 2 terminals for the input and another 2 for the output. But in the transistor we have only 3 terminals are there. One is a base, emitter, collector. But in case of we just need another one also. So that's why to rectify that one of the terminal is commonly biased for the input and output by grounding the commonly basing that. So these are the 3 types of connections for the transistor. Once again, if we need to connect the transistor in the circuit, we need 4 terminals. 2 terminals for the input and another 2 terminals for the output. So to overcome that problem, we are grounding that one of the terminal in the transistor, because of transistor having the 3 terminals. One is emitter, base, collector. So that one of the terminal is commonly used for the input and output. So that's why these are the 3 types of connections are there. The first one is a common based connection. We know that in the transistor we have 3 terminals: emitter, base, collector. In that case of we are taking the PNP transistor here, the one of the base emitter junction can be considered as a input and another one is base collector junction can be connected, because of base is commonly connected for the input and output. So that's why base is common in a input and output. Here it is that the input is a base emitter junction, means here this is the PNP transistor, we are taking that this is the emitter, collector and base is grounded, and commonly for the this input and output while we are connecting in the circuit. This is the circuit diagram. Here whenever we consider that this is the base and this one is the emitter, collector, this is PNP transistor, and this emitter base junction can be connected in a small forward bias. Already we know that the working of a PNP NPN transistor we discussed in earlier videos. So it's a small forwardly biased, means by connecting the positive terminal of the battery to the P type and the negative terminal of the battery to the this one base, then we can get that this is a forwardly biased. And to know the flow the current we just need some of the amplifiers also used in this circuit, and to get the output in this case of here load resistance can be connected, we can get the output there between the base collector junction, and it is a reversely biased. Reversely biased means here the P terminal connected to negative and N terminal connected to the positive terminal of the battery, then it is a highly reverse biased, means this one is the small forwardly biased and a collector base junction can be highly reversely biased. By using this common base connection we can get the values here. The collector voltage means whenever they are working, then we can get the output in the collector base junction, and input we can get that the emitter base junction. Then here emitter current flows through the circuit, and also their collector voltage we can get by using the voltmeter or ammeter. By connecting the voltmeter and ammeter, now we will discuss about this in the connection configurations, connection working of a configurations. Then the second type of a configuration is a common emitter configuration. Common emitter configuration. In this common emitter configuration, the emitter is common for the input and output. Common for the input and output. So input can be connected between emitter base. Means here is the emitter. This is the PNP transistor. This is collector, emitter, base. Here the between the base and emitter we can connect the input and we can get the output between the collector emitter junction. So here it is the circuit diagram for the common emitter configuration. Here is the collector means output we can get between the collector emitter junction, which is highly reverse biased, and here we can get the small forward biased. Always we know that the emitter base junction can be means a partial initially we can connect that the input can be given by the giving the forward bias, means emitter base junction can be given as a forwardly biased, small forward biased, and the second part collector base junction by using the PNP and NPN transistors, that collector and base junction can be connected in a highly reverse biased. So that's why we can get the values of current and voltage. So that's why here in the common emitter configuration, the emitter base junction can be considered as input and emitter collector junction can be considered as output. Here is that by taking this the forwardly biased and between this reversely biased we can get the values between collector and emitter biased. Here is the emitter for his input is there and as well as output also, which is connected, emitter is connected to that. Next one is third one, common collector configuration. Common collector configuration means the terminal collector will be common for both input and output. In this case, that is input is collector base junction and output we can get a collector emitter junction. Here is that this is the PNP transistor, we know that. Then this one is the base and this one is the collector and emitter. Between the emitter and collector we can get the output, and between the base and collector we have to apply the input. So in the circuit diagram also we can see this is the circuit diagram for common collector configuration. This is the common collector configuration. Collector is connected to input and output also by giving the small forward biased and the emitter collector junction high reverse biased, then we can get the current in the circuit. So mostly in this circuit, mostly we will use the common emitter configurations are for the amplification factor. These transistors can be used for the practice purpose. Mostly we will use the PNP transistor for the most of the operations and this is common base and common emitter, common collector means common collector, common base which is used for the practice purpose. Mostly we will use the common emitter configuration. Then we will discuss about that what is the common emitter configurations. There is a two type of characteristics will be there, that is input configurations means input characteristics and output characteristics. By connecting these circuits in the we can get the, if we increase the input, then what is the output? The transistor and as well as the types of a transistor and the symbol of a transistor and working of a PNP and NPN transistor, and what are the configurations of a transistor means to connect in the circuit. Now by taking the common emitter transistor characteristics means here we need 4 terminals for the connection in the circuit, 2 input and 2 for the output. So to connect that one terminal is biased means that is common in input and output. So that here we are taking the common emitter, then we need to activate the transistor. To activate the transistor by connecting in the circuit, then we are taking here NPN transistor is taken, so that here the NPN transistor, that base emitter junction can be forward biased and here the collector emitter junction can be reverse biased. Then only we can activate the transistor. This transistor is a common emitter transistor. Common emitter transistor. In the transistor, to activate that base emitter junction, the base emitter junction is forwardly biased. To measure the base current, the milliammeter is there. and to know the potential difference between the base and emitter transistor, base emitter junction, the voltmeter VBE is connected. This is a input circuit. So here, and the collector emitter junction is a reversely biased. When it is reversely biased, to know the collector current, the milliammeter is connected. This is a milliammeter is connected. To know the potential difference between collector and emitter junction is a VCE is connected, voltmeter VCE connected. Then from this changing the values of the input, then the output values also varies. So that here we are taking the values whenever it is forwardly biased by the forwardly biased with the VBE. VBE means the voltmeter. According to this, from the VBE, that is a base emitter junction is forwardly biased, and this one is a reversely biased. This one is a reversely biased. Collector connected to the positive polarity, positive terminal, and negative terminal connected to the emitter. Then only we can get that this one is the reversely biased and this one is a forwardly biased. Clear? So here the input characteristics, to study the input characteristics and output characteristics, what is the functioning is happen whenever the values are changing. Means when the input characteristics means by changing the potential at the input, we will notify the values. By changing these values of base current, by changing the voltage between the base emitter junction, we will notify the base current values, keeping the output potential, that is a VCE, keeping it constant for different values. VP connecting in different values. We plot a diagram, we plot a graph between the base current and potential between the base emitter junction. Then we will form the curves will be formed. The curves is called input characteristics. Let's see how it will be changes. We are drawing a plotting a graph between the base and this is a base current, and this is potential across the base and emitter in volts, and current in microamperes. Microamperes by keeping VCE means output voltage, output potential. That output potential keeping VCE at a constant. By changing the values of input potential, that is VBE, changing the values means up to 0 volts, 0.5 volts, 1 volt, 10 volts, the like that. Means VBE is equal to 0 volts, 5 volts, 10 volts, like that. By changing the values of VBE, and whenever the VCE is at a constant, either 0 volt or 5 volt, like that, by changing the values. Then we will note that by changing the input voltage, the values are IB current, IB values are noted. Means here, let's see, this is the 0, and by taking the values, this is the values we are measuring that. Here, by changing the values, VBE changing from this some of the 5 volts or 10 volts, by changing the values, then keeping the constant at 0 volts. Then IB current values can be noted, means VCE at 0 volts, VCE at 0 volts, the VBE values whenever the changes in from that, the current values like this will be changes. Means by increasing the IB current to base current values can be noted. And also, and another thing is the next one, changing the values of VCE means VCE another by noted of the values whenever the keeping the common potential at output VCE keeping it constant at 0 volts. By changing the values of VBE, the base current values can be noted, and after that by changing another value for the keeping it constant at 5 volts or 10 volts, 5 volts or 10 volts. Then again the process is repeated by changing the IBE values, means the VBE values, means the potential across a base emitter junction. By changing the values, again we can be noted, that is also we can get that VCE at 5 volts or 10 volts we can take that. Means here the base emitter junction values are changes, then the base current values can be noted, so that the input characteristics can be done. These curves will be formed, like these curves will be formed. The curves is called input characteristics. Input characteristics like this. Once again, keeping the collector emitter potential, means the potential at collector and emitter junction, keeping that constant at certain value. By changing the input potential, the base current values can be noted. And other, after noting at keeping that certain value of the collector base potential, collector emitter potential, then another value is fixed. Another value is fixed for the VCE value. VCE value means potential at a common emitter junction value. For certain another value we fixed that, and again that process can be done. So that the values can, whenever values can be noted, the two curves, by the values when the curves will be formed. So that the curves is called as input characteristics of a transistor. Input characteristics of a transistor. By connecting this, the small amount of base current will be connected. The small amount of base current will be formed in the circuit, flows in the circuit. Now, then by changing these values, then the output characteristics, means how the output characteristics will be changes, varies with the values of input characteristics. Let's see. Same as here, we are going to know that output characteristics. How that output characteristics will be taken, means here in input characteristics we fixed the value for VCE, and we changed the potential VBE, and we got the values for the IB, means base current values are noted, then we got the curves. This curves is called as input characteristics. Now here the keeping the base current, means by keeping IB, means base current fixed. Base current fixed means 0 microamperes and 110 microamperes and 20 microamperes, like that. Means for certain several values in input characteristics we fixed the value for output potential. Now to know the output characteristics, we are fixed the values for, to know this, to get the values for the output characteristics value, we are fixing this base current. By keeping that base current is fixed, either IB is equal to 0 ampere, 0 microamperes, either 10 microamperes. Then that VCE values, VCE changes. VCE values are changing, means in the circuit that VCE values are changing, and the collector current can be noted like this. Here we are drawing a plotted diagram, that is this is collector current in milliamperes, collector current in milliamperes, and we are plotting a diagram, we are changing the values for, collector emitter junction, that is a VCE. So that when that is 0 time from its origin, whenever IB is fixed for that value, by changing the values there is no collector current flows in the circuit for base current at keeping that constant 0. There is no current, there is no flow current, collector current flowing through the circuit. That means this region, this collector current region, means either the values are changing, goes on changing like this, means either 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here, this region when the collector current is 0, in the circuit the collector current is 0. That region is called as a cutoff region. That region is called as a cutoff region. That region is called as a cutoff region. Goes on changing the values of IB current up to 10 milliamperes, 10 microamperes and 20 microamperes, like that, by changing the values up to several times. Then we can get that values for, means either IB is equal to 10 microamperes, 20 microamperes, 30 microamperes, 40 microamperes, 50 microamperes, means IB current is fixed for certain value and changing the VC potential. Then the IC current, means the collector current can be noted for certain values. For certain values, this total region for certain, after certain values, that is collector current is independent of base current. Further certain values, the collector current is independent of its base current. Either if the base current changes, there is no changes of in collector current, then means the collector current will be independent of this current, independent of this base current. So that this total region can be considered as a saturation region. Saturation current also. Saturation current means at that current, that the collector current is independent of the base current. The current is called as a saturation current. That region is called as where the collector current is independent of the base current, is called as a saturated region or saturated current. So that here the values which can be taken further, then the region, the collector current becomes almost independent in this region, that is called as the saturated region, right? So up to some of the values, this is the saturated region. Here one function is standing, here IB is fixed for 0 value, then we changes the values for collector potential values for VCE up to some of the values we have changing, potential values are changing in volts. Then the collector current is not changing, for certain values keeping it constant. And again the collector current value, the base current is changes for 10 microamperes, again we changing the VC values, means the potential, output potential is changing. Then the collector current is also responding for that and changes with value when the fixed of the value in input characteristics IB current is at some of the fixed value. We are getting the current, collector current for certain range, and after that then we are goes on increasing the base current for the fixed value, and we are changing the values for input value, output potential, that is VCE, and as well as here we got for that certain range, certain region we then went for, that is collector current is almost becomes independent of the base current. That region is called as a saturated region, or that current is called saturated current. Here where there is no any changes of current if in case of the base current is fixed value, and there is no any changes of collector current by changing the potential of output potential VCE. Then here in this cutoff region, the two circuits, input and output circuits, are reversely biased. The two circuits, input and output circuits, are reversely biased. So that is the cutoff region. In this cutoff region, the input and output circuits are, both circuits are reversely biased. In the saturated current, the input and output circuits are forwardly biased. So that the current does not depend, that means the collector current is independent of the base current when the two circuits are forwardly biased. And whenever the remaining region which is having that this depends on the total region, the total region depends on the base current. Whenever the base current is fixed value, by changing the output potential, then the collector current is flowing through the circuit. Then the total region is called as a active region. Active region. Active region. So this is how we got the curves. We got the curves. This curve is called as the output characteristics. Means by changing the VCI values, IC values, IC current means collector current can be noted. For fixed value, fixing the values, fixing the IB values of different. Means here VC values are changes for up to 0, 5, 10, 20 volts like that. By changing that, the collector current can be notified, means the output current can be notified. Once again, here where the collector current in that region, the collector current is almost independent of the base current when it will be happen when the input and output circuits are forwardly biased is called as a saturated region, saturation current. The current flows through the circuit is the saturation current or saturation region. That region is called a saturation region. Where the collector current, there is no collector current is almost 0 in the circuit. That is called as when the changes of the potential also, the collector current is 0 in the circuit is a cutoff region. When that will be happen in when the input and out, that is called as when the input and output circuits are reverse biased. And the remaining journey wherever the base current, collector current and output potential depends on that. By changing the output potential, the current will flow to the circuit by the changing for the fixed values of IB current. Then that region, total region is called as a active region. Active region. In that case, the values can be in output characteristics. We got the 3 regions for the conduction, means whenever the current flowing through the collector current is almost 0 in the cutoff region when the base current is 0. For the fixed value base current is 0. By changing the output potential is also, then there is no current flows through the collector current flows through the circuit. So that is called as a cutoff region. And as well as at the sum of the stage, at the sum of the values, then collector current will be independent, almost is independent of the base current. When it will happen when the input and output circuits are forward biased, that region is called as a saturated region. Means whenever the current is flowing, some of the characteristics whenever the values are changing goes on, then at some stage there is no change in collector current. After that, if the base current is changes, the collector current will be independent of that region. Means at that stage the saturated region, that region is called as a saturated region, which is collector current is independent of the base current is almost. That region is called, this will happen whenever the both circuits, means both junctions, that emitter junction and the collector junction, means input junction and output junction, both junctions are forwardly biased. Then that region is called as a saturated region. And the next one is when the collector current is almost 0. When the collector current is almost 0, this happens when the input and output junctions are reversely biased. That region is called as a cutoff region. And as well as means whenever this region means there is no current flows through the circuit, this region is called as a cutoff region, and this region is called as a saturated region. And the remaining region, which is the input region, input junction is forwardly biased and output junction is reversely biased. By the collector current changes, by the collector current changes rapidly, means by the changing in the base current. Even though the small change in the base current, the large amount of output current, means collector current changes in the circuit. So that here the many times the collector current is greater than the base current. So that's why here by changing the small change in the base current also large change in collector current will be happen. This happens when the input junction is forwardly biased and output junction is reversely biased. Means the emitter junction is forwardly biased and the collector junction is reversely biased. Then so that region is called as active region. That region is called as active region. In that region, whenever the transistor is works as an amplifier, means whenever we use the transistor whenever the transistor is operated in active region, the transistor is used as a amplifier. Amplifier whenever uses, so that the input characteristics and output characteristics, by taking these values we can get the parameters of transistors. Means by connecting the transistor we can get the values, but by changing the input values the large amount of current flows through the output value, we can get that. So to know the resistance, however the input resistance is there, and at the same time output resistance, and as well as how the current, AC current gaining and DC current, those are the parameters which is can get from the input and output characteristics. Those are the parameters of transistor. First of all, input dynamic resistance. Input dynamic resistance means whenever by keeping the collector emitter junction, keeping it constant, the ratio of emitter base junction, the emitter base junction means here the potential, means the emitter base junction means the potential difference between the emitter base junction to the base current, change in base current, change in the emitter base junction potential difference to the change in base current, keeping the current emitter potential at a constant, keeping the collector emitter junction potential is at a constant, then that is called input dynamic resistance. It can be denoted with R suffix I, then Ri is equal to delta VBE by delta IB. Here delta VBE be the change in potential across a base emitter junction, and delta IB means the change in base current when by keeping the collector emitter potential constant, collector emitter junction potential constant, then we can get the ratio of, once again the input dynamic resistance definition is the ratio of the change in potential of base emitter junction to the change in base current, keeping the collector emitter potential at a constant, collector potential junction at a constant. Then this is about input dynamic resistance, one of the parameter of transistor, and another one is output dynamic resistance. This is also same, but here the keeping the base current at a constant, the change in potential across the collector emitter junction, the ratio of the change in potential across a collector emitter junction to the change in collector current is called output dynamic resistance, by keeping the base current at constant. Simply the ratio of change in potential across a collector emitter junction to the change in collector current by keeping the base current at constant is called output dynamic resistance, and next one, the current amplification factor. Also we can get the AC current gain, whenever the two circuits are working, then by the input and output characteristics we can get that the change in output current by the change in input current. That means to say the change in collector current, the ratio of the change in collector current to the change in base current by keeping the collector and emitter potential at constant. The voltage at a collector emitter junction keeping it constant, the change in collector current, the ratio of change in collector current to the change in base current is called current amplification factor or AC current gain. That is denoted with beta suffix AC. Then because of AC current is gain, so current gain can be denoted as beta. So that the change in collector current, the ratio of change in collector current to the change in base current by keeping the potential at collector emitter junction keeping it constant, that is a current amplification factor or AC current gain, that is denoted with beta AC. Again the next parameter is a base current amplification factor. Also this can be called as a DC current gain. DC means direct current gain, that is denoted with beta DC. Current gain always know that beta is the beta DC means the collector, the ratio of collector current to the base current is called base current amplification factor or DC current gain. That is beta DC is equal to IC by IB. This is about base current amplification factor and the common emitter transistor characteristics, input and output characteristics. What are the regions it can be formed whenever the regions means the saturated region, cutoff region, active region. Whenever the transistor is applied means operated in active region, that acts as the amplifier, and whenever that is will be happen in a cutoff and saturated region, it will act as a switch and oscillator also. So that here it is that this is about common emitter transistor characteristics. Next we are going to discuss about what is the transistor devices. By the transistors as a devices like amp switch, amplifier and oscillator, like that. Transistor when the characteristics and means how the transistor can be operated and what is the input characteristics and what are the output characteristics. By operating the transistor in such a way, we got the three regions means by changing the potential, keeping the output potential at constant, and we got the region, some of the regions, that is a saturated region, cutoff region and active region. While the transistor is operating in a cutoff or saturated region, that transistor can be used as a switch. So a device switch means a transistor as a device. Like this is the circuit diagram. Let's see. Here we are taking the NPN transistor. In the case of NPN transistor, there is a common emitter configuration, common emitter biased transistor we have taken that. So that's why in the input and output also the emitter is biased, means in the input we connected that is a VB from the battery. From the battery we are giving the input, and so that's why the VBB is considered as a input. The potential is given to the transistor. This is a base. To find out the base current, that is IB, and some of the resistor is connected, and that is RB, means the resistor base resistance. And to know the potential difference across the terminals base and emitter, this will be the potential across VBE voltmeter, and the IE means the emitter current, and this will be the IC means collector current, which is given by the, this is forwardly biased and this is reversely biased, and whenever it is operated in cutoff and saturated region, then whenever it is in saturated region, that is the two circuits, so primary circuit, first primary circuit, input circuit and output circuit, both will be in forwardly biased, and whenever that it is operated in cutoff region, then both will be in reverse bias. So that's why we can get the values of output character, output values we can get. Here that according to the Kirchhoff's voltage law, whenever the algebraic sum of all the potentials at a junction is 0, from that using Kirchhoff's voltage law, we can get that the input and output circuits like this. Here, that is for the input, the base bias means the base bias, voltage base bias, if we taken that, here the VBB base bias can be taken as input. So that's why here in the according to the directions the base bias is in this direction, so that's why that will be the negative, the potential is taken as negative minus VBB, plus the direction will be taken like this, so that's why that is RB IB, this potential V is equal to IR, so IB RB taken as positive, and this is also taken as in this direction. So that's why minus VBB plus IB RB plus VBE is equal to all the potentials algebraic sum of the circuit. This circuit is equal to 0. So from that VBB is equal to VBE plus IB RB, that VBB considered as input, so that's why we can say that VI is equal to VBE plus IB RB. So that potentials means here we are taking that, then here we are taking the silicon transistor. For a transistor, silicon transistor is about that has to operate in up to 0.6 voltage whenever it has to give the output. More than the 0.6 volt or 0.7 volts, so then only less than the 1.0 volts, then only the silicon transistor will be an active region. So that here the silicon transistor is about to 0.6 volt to 0.7 volts, not more than the 1.0 volt. Then whenever we gives the less than 0.6 volts, the transistor, into the transistor, the output will become 0. There is no current flows in the collector, current flows in the circuit. So that's why the silicon transistor is about to its base emitter junction potential will be 0.6 volts. Whenever we give the 0.6 volts, beyond the 0.6 volts, then only we can get the output, some of the values we can get. Here then for the, this will be the for the input circuit, and for the output circuit if we take the here the VCC minus VCC plus ICRC, because of this in this direction the sum of the resistance in opposite direction. So that's why we are taking that according to this, that is minus VCC plus ICRC plus VC is equal to 0. The total potentials, algebraic sum of all the potentials, which is equal to 0. From that equation also we can get that the VC, the output which is taken from the VCE, output voltage, potential difference across the terminals collector and emitter. So that's why we are taking the output from this. So that's why VC is taken as output. So from that output VC is equal to VCC. Whenever taken this side, VCC minus ICRC will be the output voltage. From this output voltage, assume that VC is equal to output and VBB is equal to input. So VBB is equal to input, means whenever we give the input voltage, then we can get the output voltage like that. In case of the silicon transistor, if the potential is given less than 0.6 volts, less than 0.6 volts, this is so that's why there is no collector current flows through the circuit. If the potential given in input, that is in Vi is equal to the potential given to the input, is less than the 0.6 volts, no collector current in the circuit, the collector current becomes 0. So that's why IC is equal to 0. Then the output, what will happen? Output whenever the IC is given, then IC is equal to 0, then VC is equal to output VCC, means V is equal to, here V0 is equal to VCC minus ICRC, means output voltage. This is output voltage and this is input voltage to find out that. So from that output, by substituting IC is equal to 0, we can get that V0 is equal to VCC. And whenever if more than the 0.6 volts is given to the transistor, means beyond the 0.6 volts up to less than 1.0 volt, means between the 0.6 volts to up to 1.0 volts, then but less than the 1.0 volts, some collector current flows through the circuit, some collector flows through the circuit, but we can observe that the output voltage will be decreases. Whenever the increasing of the input voltage, then output current increases, means the collector current increases, but the potential V0 decreases, because of here VCC has fixed value. So that's why from the fixed value, whenever we taking that IC is increases, then by decreasing this V0 will be decreases. Because of here is that the more addition is there, the potentials will be added, because of the potential is also increasing, so that base current is increasing. So that way output collector current, there is no, whenever we give the more than 0.6 volts, less than the 1.0 volts, then the collector current increases in the circuit, but we can observe that the output voltage goes on decreasing. Due to that, here value of V0 decreases with increasing the Vi beyond the 0.6 volts, means like that up to 0.6, 0.7, 0.8, up to 1 less than 1.0, more than that, whenever the input is given nearly 1.0 volts, when the beyond the 0.6 volts nearly 1.0 volts, so we applied the input, then we can observe that the input collector current will be goes on increasing linearly with the output, up to less than the 1.0 volts, from 0.6 volts to up to less than 1.0 volts. 1.0 volts. Then input and output goes on linearly. Then here the linear, whenever it is a transistor will be in a active state. Means whenever the input is given less than 0.6 volts for the silicon transistor, it's a cutoff region. It will be in a cutoff region. If in case of more than the 0.6 volts to the up to 1.0 volts, the silicon transistor will be in a active state. So here the Vi and V are linear, means input and output voltages are linear. Then if the voltage, input voltage given more than the 1.0 volt, the input and output voltages will not be linearly. Whenever the collector current is increasing and goes to the maximum value, the output value will be goes on decreasing it towards the zero, but never becomes a zero. That will goes towards the zero, but never becomes a zero. Means here collector current will be maximum, IC will be maximum, but the output voltage never becomes zero, but is towards the zero, it will traveling towards the zero. That will be there whenever the collector current is maximum. That region is considered as a saturated region. That is a saturated region. Once again, this is a three things are there. One is cutoff region. We know that already we discussed in the transistor characteristics, common emitter transistor characteristics, common emitter based. In that case of first one is the cutoff region and a saturated region and active region. In this case also the three regions can be noted. First one is whenever the transistor is input is a silicon transistor we are using, which is having its potential difference 0.6 volts. Whenever the potential is applied more less than the 0.6 voltage, then IC current means the collector current becomes 0. The output voltage we can get will be the maximum it will state. So that will be the cutoff region. And whenever the voltage more than the 0.6 volts, greater than 0.6 volts, less than the 1.0 volt, then that Vi and V0 means the input and output voltage goes on linearly. That will be the active region. And if the beyond the 1.0 volt means more than the 1.0 volt if it increases, then input and output voltages will not be linear. Because of increasing the input voltage, we can observe the output voltage goes on decreasing, it will towards the zero, but never becomes zero when the collector current is maximum. When collector current is maximum is considered as a saturated region. That saturated region means here the three types of saturated points, the saturated point and active state and at the same time cutoff regions. So if you draw a plot a graph between the input and output characteristics, input and output values, then we can get that why the transistor will be operated between the cutoff to the saturated to cutoff. Means the input and output voltages, output voltages considered between the certain voltages, the values will be varies, input and output values will be changes between the certain voltage limits. So that's why here by plotting the graph between the input and output voltages, we can get the clear idea how the transistor will act as a switch. Whenever plot a graph between the input and output voltages, we know that silicon transistor beyond the less than the 0.6 volts will be in a cutoff region. Means if in case of Vi is low, input is low, means less than 0.6 volts, means less than 0.6 volts, input is less than 0.6 volts, then output is high, up to in these points the output is high. This region is considered a cutoff region. That is a cutoff region, and in this case the transistor will not work. The transistor not working in the proper, so it can be considered a transistor in switched off condition, switched off state. less than the 0.6 volts, silicon transistor will be in switched off state, and the output is a maximum. Transistor is switched off. In case when input is low, that is transistor is switched off. If input is high, means more than the 1.0 volt, more than the 1.0 volt, then here output will be low like this. Here is maximum. Whenever the current here the voltage is 0.6 volts, if output is maximum. Whenever it is increased by that 1.0 volts, that voltage goes on decreasing. Voltage goes on decreasing, but never becomes zero. That current will never become zero. The Vi is low and collector current is maximum. The collector current is maximum and transistor is fully conducting the current, collector current flowing through the circuit. So that's why here it is said to be there in a switched on condition. Means if in case of the input is high, the transistor is in switched on condition. So that Vi is high, the transistor is switched on, and Vi is low, means input is low, input voltage is low, then the transistor is in switched off condition. So this indicates that the transistor acts as a switch from the cutoff to the saturated to the cutoff region. By transferring that, then transistor acts as a switch. So that the transistors are made up of in this case the never be stays in active region. It will be operated between the saturated and cutoff region. It will be operated to the saturated and cutoff region. So that's why we can say that the transistor acts as a switch. Transistor characteristics and input and output characteristics, how the transistor will activate. In that case, we got the three regions like saturated region, cutoff region, and as well as the active region. And after that, how the transistor acts as a switch. Whenever the transistor is operated between the cutoff region and saturated region, whenever it is operated in cutoff and saturated region, whenever that transistor will act as a switch. Now means when the transistor acts as a in cutoff region as a off position, if in case it is operated in a saturated position, it will be considered as a switched on position, and earlier we discussed about that switch. Now if the transistor is operated in active region, then that acts as a amplifier. Transistor is operated in a active region, then that acts as a amplifier. What is amplifier? Means for example, while we are speaking in the microphone, our voice is less, but when we are talking in the microphone, we can hear the loudness of sound from the loudspeaker, more sound from the loudspeaker. The signal which is sent by us is amplified. That process of increasing the signal, the process of increasing the strength of a signal is called as amplification. The device which is used to increase the or raise the strength of the signal is called amplifier. When the transistor is operated in active region, then the transistor acts as an amplifier, uses an amplifier, and when the process of raise the strength of a signal, the process of raising the strength of a signal is called amplification, and the device which is used to increase or raise the strength of the signal is called amplifier. Here transistor as the amplifier, commonly for the amplification process in the amplifier, common emitter biased transistor we can use most commonly. So here this is the block diagram of amplifier. So here whenever the microphone which is used to like this is the microphone which is used to speak, and whenever we are giving the signal to this mic, means microphone, the signal is sent to the amplifier. The signal sent to the amplifier, and that amplifier will increase the strength of a signal. Amplifier increase the strength of a signal, and that amplified output we can hear from the loudspeaker. We can hear from the loudspeaker. This in the radio signal transmission, means a radio communication process like antenna. Whenever the signal is sent by that, the antenna received the signal is very less. Whenever the received signal by the antenna is very less. Whenever the less, in case of watt, in case of means the signal will be maybe watt. So that if you want to hear that sound, the signal has to increase the hundreds times of that input signal. So here we can see that whenever the signal sent to the microphone, which is received by some of the receiver in a watt, a small size of signal, that can be amplified by the amplifier. In radio communication also, in visualization, means everywhere we are using the amplifier. Everywhere we are using the amplifier for the sound wave versus the picture also. Whenever the signal strength is increased, for example, if in case of nowadays we are getting the DTH box, right? So setup box. In setup box also, whenever the signal is received by the setup box, some of the HD box also there, some of the normal box also there. Whenever we get the HD channels, means HD channels means we can see the more clear than the normal. Means high definition, means high signal it can be received. It can be received. Means the signal amplified, the strength of the signal is increased by the amplifier. So that in case of that, whenever the amplification means the strength of the signal can be increased, the strength of the signal can be raised. So that process is amplification, and the device which is used for that process is called amplifier. This is microphone, and the signal whenever sent to the microphone, and it is say microphone sent the signal to the amplifier, and through the amplifier that sound signal or some whatever the signal we are giving the input, the input signal is amplified. That amplified output given to the loudspeaker, which can hear 100 to 1000 times of more sound whenever we can get. So that what is the working of, mainly we will use that, mainly commonly in the amplification process, the common emitter transistor can be used mostly. So that what is the common emitter transistor? This is the circuit diagram for this is NPN transistor we are taking that is common emitter configuration, means this is emitter, this is base, and this is a collector. So that here there is two type of amplifiers is there. First one is the current power amplifier, and another one is a voltage amplifier. In this case of what is power amplifier? Power amplifier means which can increase the strength of the power, means raise the power level, and according to the voltage amplifier which raise the voltage level. Then the working of a transistor as a amplifier, working as a transistor as amplifier. We know that the input and output characteristics of a transistor according to the common emitter configuration. By giving the input signal, whenever, once again I will repeat in fast forwardly. So whenever the input signal given to this, by changing the potential difference, by keeping the VCE at constant, by changing the VBE we can measure the base current. And as well as here is also by keeping the fixed value at the IB, means current here which is passing that is IB, means base current getting fixed, making keeping the base current fixed, and we can see we already draw the graph between the VC and IC by measuring changing the fixed value of IB. We can change the VC, by that we can measure the collector current which is in the circuit. So that by changing the input signal is to be amplified connected with the VBE in seriously, means AC input which we are giving that connected in series connection, and so that with the biasing battery VBE, this one is the biasing battery VBE, this is VBE biasing battery, it is connected in series, and as well as a loud RL resistance, means this is RL resistance, this is input resistance. This is input resistance, this is RL resistance. Wherever load resistance, it can be called as a load resistance. RL means load resistance is connected in the collector circuit. This is primary circuit, this is base emitter circuit, and this is collector emitter circuit. This is the primary circuit and this is the secondary circuit. In the primary circuit, the load resistance is connected in the collector circuit. As the potential difference VBE changes with the time, collector potential difference across the between the base and emitter. Emitter is common biased, so that's why here the potential difference VBE changes with the time due to input signal base current IB and collector current IC and output voltage VC changes accordingly. Means whenever what is meant by the active region, in the active region the base emitter junction can be forward biased and collector emitter junction can be in a reverse biased. When if the transistor in active region, in the whenever it is happen, when it happens that is a base emitter junction will be in forward bias, means primary circuit is in forward bias, and the collector emitter junction means the secondary circuit junction will be in a reverse bias. Then only the transistor will be in active region. So that's why here whenever the VBE changes, means potential difference between the base and emitter junction changes, so that according to that the base current and collector current and potential difference between the collector and emitter junction, base current, collector current and potential difference between the collector and emitter will be changes accordingly, so that the signal can be amplified. Here the input and output voltages are both in opposite phase. Input and output voltages are both in a opposite phase, so that here we can get the negative sign whenever the voltage gain. In the voltage gain we can get the negative sign, so that here the once again when the potential difference across the base and emitter changes, means VBE changes due in time with the time, then according to that IB means base current, collector current and potential difference VCE changes accordingly, so that we can get that current gain. We can get the values from this current gain. What is meant by the current gain? Current gain means is nothing but already we discussed about it, the ratio of output current to the input current. What is output current? Here the collector current is the output current. What is input current? Input current is the base current. So that the change in output current to the ratio of change in output current to the change in input current is called as a current gain, that is denoted with a beta. Here current gain beta, the ratio of change in output current to change in input current. That current is AC current, alternating current, so that the input current is IB and output current is IC, so that the ratio between the change in output current alternating current to the input alternating current is called a change in input alternating current is called as a current gain. So that here we can get that current gain can be denoted with beta. So beta is equal to delta IC by delta IB. Delta IC means change in output current by delta IB means change in input current. So here once again, when amplification means to increase the strength of a signal, the process is called as amplification. The device which is used to raise the strength of the signal is called as a amplifier. Whenever amplifier is commonly in the amplification process, the transistor which is a common emitter transistor can be used, and as well as there is a two type of amplifiers is there. First one power amplifier and voltage amplifier. The power amplifier is to raise the power level, and voltage amplifier is used to raise the voltage level. So that in that working process, whenever the VBE changes, when the VBE changes, the input AC input is connected seriously with the battery VBE, so that whenever the potential difference between the base and emitter changes with the time, with the time in due to input signal, that is base current and collector current, and potential difference between the VC, potential difference between the collector and emitter will be changes accordingly, so that we can get the current gain and the voltage gain and power gain. So that the current gain is the ratio of change in output AC current to change in input current is called a current gain. The next the voltage gain. The voltage gain. In that voltage gain, we can see that here already we discussed about the current gain. In the voltage gain, we know that the ratio of output voltage, the ratio of change in output voltage to the change in input voltage, that is, we know that voltage means output voltage will be VCE and input voltage will be VBE. So the change in output voltage is delta VCE by delta VBE. Here we know that voltage V is equal to, already we discussed about that, V is equal to IR from Ohm's law. According to the Ohm's law, V is equal to IR. So that in case of VC, in output current, we know that the voltages are in a opposite phase. So that's why we can get that whenever the collector emitter junction voltage will be in minus IR. So that's why according to this, output voltage means I means output current, RL means load resistance. At output resistance we can get that, from the signal we can get that output signal, AC signal. Then here minus RL of delta IC means delta VCE is equal to, means here delta VCE is equal to, in delta VCE voltage means the current is IC and delta IC, current change in current delta IC, and resistance will be RL. So we got that it is in negative phase, so that's why negative sign we can get that. So minus RL into delta IC by input VBE. VBE means what? Here the input potential difference, it is at the input potential difference across the base and emitter junction. So that's why here input voltage is a delta VB, change in input voltage is a delta VB. So that's why here delta VBE is equal to input resistance is RI. RI is the input resistance, and delta here current will be delta IB, input current will be base current. So that's why RI into delta B. So from that equation we can get that. But we know that from the current gain, beta is equal to delta IC by delta IB is equal to current gain. This is delta IC by delta IB. From that equation we are substituting, then we can get minus beta into RL by IRI. RL by RI remains constant and remains same, and delta IC by delta IB is equal to beta. So minus beta into RL by RI. So that the negative sign indicates that the input and output voltages are in opposite phase. Opposite phase. That is, input and output voltages are in a opposite phase. So here this is about a voltage gain. The next one is a power gain. Power gain means the power is equal to, we know that is a P is equal to V into I. P is equal to V into I means voltage into current or current into voltage. So that's why here power gain means it is denoted with the AP, the ratio of output power to the input power. The ratio of output power to the input power is called a definition of power gain. So from that equation we can get that power gain is equal to current gain into voltage gain, means IV means power gain into voltage gain. From that equation we know that output power by input power. Output, what is output power? Current gain into voltage gain means I out by I out into V out. This is the current gain out, I out by into V out. So at the same time current gain means current out by current in, input current and output current. Voltage gain means output voltage by input voltage. So from that equation we can write that here we have that beta RL by RI and as well as a delta IC by IB. We know that is equal to beta, beta into beta, beta square into RL by RI. This is about power gain. So whenever the transistor is operated in active region, then the circuit will be in forward bias. The primary circuit will be in forward bias, means emitter base junction is in reverse forward bias and collector emitter junction is in reverse bias, so that it happens in active region. In active region, so that whenever it is operated in active region, transistor acts as a amplifier, transistor as an oscillator. In before video we discussed about transistor as an amplifier. Now we are going to discuss about transistor as an oscillator. Oscillator. Oscillator means it's a device which is converts the DC into AC. DC into AC. And that oscillator consists of a three parts mainly. In that case, here these are the three parts. First one is a LC circuit. This is the LC circuit, and here inductance and capacitance are connected in parallel to each other. This is called as a tank circuit also. This circuit is also called as a tank circuit. Tank circuit. And this coil is called as a tank coil. This is a LC circuit and a transistor amplifier. Second one is a transistor amplifier. This is transistor amplifier, and it is connected as the forwardly biased, and the collector region is connected as a reversely biased. And third one is a positive feedback circuit. Positive feedback circuit means whenever the connected, here L is the one of the inductance and another L is the, this is called as a tickler coil. Tickler coil. And there is some of the feedback is connected to with the inductor, and this with this inductor tickler coil to the tank coil. Due to the mutual induction of this, whenever in the circuit the key is switched on, means connected key is in the circuit connected, then the collector current will passes through the circuit, so that the L is also the base current increases as well as the collector current increases, so that due to the mutual induction of this feedback, due to the mutual induction of between the L dash and L, and EMF is induced to L, and EMF is induced to L. When the key is connected, then here the collector current passes through the circuit as well as the base current is also increases, base current and the collector current and increases, so that due to the mutual induction between the L dash and L and the tickler coil and tank coil, due to the mutual induction, and EMF is induced to the L. This will charge the upper plate of the capacitor positively. The upper plate of the capacitor conductor positively. Whenever it gets positively charged, this process is continuous, and again this due to the collector current, this L dash is also come to the maximum value. Due to the mutual induction, this is also charged, and due to the charging, the capacitor's upper plate will be positively charged. Whenever it is forwardly biased, then the base emitter current, whenever they say the forward biasing, it supports the forward bias, means the base emitter junction will be forwardly biased. So that's why this, whenever it gets due to the mutual induction, EMF is induced, means a magnetic flux is induced, magnetic flux is linked. So that due to the mutual induction, it is induced and it increases the charge, it tries the charge of positive, it is charged positively charged the upper plate of the capacitor, so that it supports the forward bias, a base emitter current will be passes, so that emitter current and collector current will be increases, that emitter current and collector current will be increases. So that increment of emitter current and collector current, this L dash tickler coil comes to the maximum value. When the collector current becomes saturated, means come to the maximum value where the transistor comes to saturated state. When the collector current becomes maximum value, then the transistor comes to the saturated state. When it comes to saturated state, it is saturated, then this L dash comes to the steady value, it links the steady value due to the mutual induction, then there is no magnetic flux is discontinued. Because of there is no increment of this one, it comes to steady value. Because of IC means collector current comes to the maximum value, it doesn't increase, so that's why this saturated transistor comes to the saturated state. so that there is no any increment of this L dash, so that this due to mutual induction the induced EMF is the magnetic flux linked with this one can be discontinued, so that the L dash, the L inductance will be goes on withdrawing the charge, decreasing the charge, so that the here the current, emitter current and collector current is also goes on decreasing, and which the linked magnetic flux linked with the coil L will increase the charges the down plate of the capacitor, lower plate of the capacitor, so that the forward bias is opposed. The forward bias is opposed the decrement of the emitter current, decrement of the decreasing the emitter current, which opposes the decreasing the emitter current and collector current. If the forward bias is removed, then this collector current comes to 0. The collector current goes on decreasing and comes to 0, and this lower plate will be positively charged. Means whenever the collector current becomes 0, it comes to the cutoff state. Again, this process can be repeated. Whenever the keys is going on, then this will be positively charged, it is forwardly biased and it is reversely biased, so that's why it is forwardly biased due to the collector current and emitter current will be increasing circuit, and it is due to the mutual induction, then it is also charged, so that's why the upper plate can be charged positively. It becomes maximum more positive charge whenever the collector current increases in the circuit due to the mutual induction, and EMF is induced to the L. Here we can get the output, so that whenever it gets due to the mutual induction and EMF is induced to the L, and the magnetic flux is linked with this the feedback, then the upper plate of the capacitor is more positively charged until it reaches whenever it reaches the saturated state, the transistor comes to the saturated state, then the collector current becomes maximum, then the tickler coil will having the steady value. So that whenever it comes to the steady value, after that, when the magnetic flux which is feedback is discontinued, so that the inductance is discharged means the capacitance, the positive charge is discharged in the support of the inductance. The capacitor is discharged with the support of the inductance, inductor L, so that due to the linked with the magnetic flux is linked with the tickler coil is the lower plate of the capacitor can be positively charged. So that's why here the forward by whenever it is getting positively charged, it is charged, upper plate is positively charged, which will support to the forward biasing of base emitter junction, base emitter current. So that here whenever it is positively charged, then the forward bias is opposes. So that here there is no further decrement in the collector current. By avoiding the forward bias, when the collector current becomes 0 and it will comes to the cutoff region, and means the transistor comes to cutoff state. This process is going on from the cutoff region to the saturated, saturated to the cutoff, cutoff to the saturated due to the mutual induction between the tickler coil and tank coil. Once it is having the steady value, whenever the collector current becomes maximum, when it will transistor comes to saturated state, and this will be discontinued, and after that, after discharging the capacitor supply plate by the support of the inductance, due to the link the down lower plate of the capacitor can be positively charged, which forward bias is opposed for the decrement of the current in the circuit. Then by avoiding the forward bias, the collector current becomes 0. Means that come from the saturated state to the transistor is comes to cutoff state. This oscillations will be happen. This transistor amplifier, the transistor amplifier will increase the DC lower DC voltage to the DC lower voltage of AC to the into higher voltage of AC. The transistor amplifier will increase the low voltage of AC into the high voltage of AC. So that here the three parts will be works like this. The LC circuit due to this circuit, the oscillations will be happen from the cutoff to the saturated, saturated to the cutoff state. The oscillations will be happen. The frequency of oscillations can be F is equal to 1 by 2 pi root L by C be the, already we discussed in alternating current and electromagnetic waves, the inductance and capacitance, about the inductance LC circuit in the earlier units, in alternating electricity, alternating current and electromagnetic waves, about the LC circuit we have studied about it. So that it is also, that LC circuit is also known as the tank circuit. In this coil is called as tank coil. And of here the inductance and capacitance in the circuit, the frequency of the AC output will be. This is frequency F is equal to 1 by 2 pi root 1 by LC be the oscillations whenever this feedback is given to that. The feedback is given to that. The transistor once comes to the saturated state, whenever the collector current is flowing through the circuit, whenever the key is switched on, then after it will comes to the maximum state, collector current becomes maximum, means the transistor come to saturated state, the mutual induction will be no role to play. The magnetic flux is linked to with the L dash is also L with the L also no role to play. So that way it is goes on, the capacitor supply plate goes on decreasing, it's a discharging with the support of inductance, so that we can get the output from the here. And also the lower plate of the due to the magnetic flux linked with the coil, it will charge the lower plate of the capacitor. So that's why the forward bias which opposes the decrement of charge current in the circuit. So that by avoiding this one we can get that once it is easily positively charged, again we can repeat this process from the collector current becomes 0, it comes to the cutoff region. This process can be done between the saturated point state to the cutoff state continuously. So that there is several type of the oscillators are there, then Harpitz oscillator and Hartley oscillator and Corpitz oscillator, like that. By correcting this the tank circuit in the base biased, then base oscillator we can say, and whenever it is connected to the collector, and it can be called as a collector oscillator. So that's why this is about a feedback amplifier or and once again the transistor amplifier already we discussed what is positive feedback circuit. Due to the resistance of the circuit, which is having the resistance, small resistance, internal resistance having by the circuit, due to the resistance of the circuit, some of the electrical energy is converted into the heat energy. To compensate that one, the loss of that a fraction of output feedback from this, the loss of a fraction of output feedback into input circuit by using a inducting coil. If the feedback is in phase, the input that known as a positive feedback, means whenever it is converted from the electrical energy to the heat energy, to avoid that feedback, output feedback in the output feedback, then we will use that another coil. This, if it is in the same phase, then that can be said as let's say positive feedback. This is about a transistor as an oscillator. About the transistors and PN diode, and as well as whenever the transistor used as a switch and amplifier, and we discussed about the oscillators also. Now we are coming on to the another topic, the most important topic in for nowadays we are severally using in the electronics. Those are about the digital signals. What is meant by the digital signals? A signal, either voltage signal or current signal, is having whenever they are having the two discrete values are called digital signals. Means whenever the signal, either voltage or current signals only having the two discrete values, those are called as digital signals. The process means which is the devices or the process which analyze or generate, which has to transfer the signals by the devices are called the logic gates. Means digital signals which is using for the electrical circuit. Means here we are given an electrical circuit based on some logic and connected between the inputs and outputs. That means to say here, when the circuits which are used to process digital signals, means Here a circuit which is used to process the digital signals. Already we have told you what about the digital signals. Whenever the signals are having that only two discrete values are called as digital signals, and a circuit which is used to process the digital signals are called logic gates. Here the logic gates are based on that Boolean algebra. Because of he invented that Boole, he invented the logic gates about that. So that's why whatever the resultant, whatever the output we can get there, that is called the equation or called as a Boolean algebra. According to to analyze the output values by giving the input values, here the logic gates based on the Boolean algebra, so that's which is having the two values only, which are having the two digits. Those are 0 and 1. Here also signal is having that according to the based on this numbers, that is 2 digits, that is 0 and 1 binary digits. So this is about according to this binary digits 0 and 1, what is and 3 operators can be operated by the digital signals can be operated by the 3 operators. Those are OR and NOT, OR and NOT. These 3 operators can be operated the digital signals by the gates. We can analyze that the outputs by drawing here truth tables, between the input and output whenever it is having there. When the logic gates are having the 2 or more input poles, and as well as the one pole is the output signal. So that in case of whenever the input is given in OR or a NOT gate, the meaning of 0, if we give the 0 input to the one of the terminal of the gate, then what about the meaning of 0? 0 means it's a false or off or low or open. These are the meanings, or no. These are the meanings of 0, which is gates operated by the digital signals, which is having the 2 digits, that is those are the 0 and 1, which is operated by the 3 operators, those are OR and NOT, those are the operators. By using this one we can construct the gates. So that here the meaning of 0 and 1 is the 0 is a false, off, open, means here false, off, open, low, no. These are the meaning of 0, and the meaning of 1 means true, on, S, close, high. Means here we are taking that values for here. Let's see here once the values which is given to that, we can state it's a true or false in logic. That is a true or false in a logic, true and false in a logic. And as well as here the on and off are in electrical circuits, on and off in electrical circuits, and as well as here 0 and 1 in mathematical sense, 0 and 1 in a mathematical sense. Means here we are taking that whenever the input is given in true or false system, then that can be considered in logic. And whenever if we give the on and off, that will be in the electrical circuits, means switched on and switched off like that. And if we give the 0 and 1 in a digits, then that will be the mathematical sense. Whenever we give the logic sense, then true or false, then it can be there. States that true means it's a switched on, false means it's a switched off. We are not connecting anything. The open means in this case of we are discussing about that, this is about logic gates. In that logic gates the 3 operators are there. In that first operator is a OR. Let's see what is the operators and gates. According to the Boolean algebra, there is the operators and gates. This is the OR operator. OR operator is basically used for symbolically for the addition. Symbolically we use for the addition, used to addition symbolically. It is represented by the plus. For addition, A and B means here we can see that there is a 2 signals are there, consider it's a A and it's a B. It's a A and it's a B. So here A B, one we can write that the resultant whenever it is a Y is equal to A plus B. Here this is the Boolean expression, Boolean algebra expression, Boolean algebra expression. So here it is that we can read it as A or B. A plus B can be read as A or B is equal to Y. This is the Boolean algebra. Whenever the addition symbol we get the between the two A and B inputs, then A or B is equal to Y according to the Boolean algebra. Further, in case of the OR operator, this is the circuit, electrical circuit of the OR operator. Let's see how this operator can be gives the output values. Here, that according to the truth tables we are drawing. Let's see. First of all, inputs we are giving that. Inputs means it is already biased. So whenever it is A is open, switch 1, switch 1 S1 and switch 2 is S2. So both are open. Can the conduction is there? No, because of whenever it is comes to it, current is flowing through the circuit. This is also open and this is also open. There is no connection between the output and input terminals. So that's why it is also open and it is also open. So that's why can the bulb glows? No. So no bulb glows whenever the both switches are is in open. The next output, the next input is open. Switch S1 is open. It is opened and switch S2 is closed. Means whenever the switch S2 is closed, then the conduction will be happen through the S2. Because of S1 is open, there is no conduction through the S1, and in that case the S2 is closed. S2 is closed, so that's why the conduction will be happen through the S2 and bulb glows. Because of the conduction is there. So that's why S2 is a bulb glows. Yes, bulb will glows. The next one, input S1 is closed. S1 is closed and S2 is open. S2 is open. Then whenever this goes, then power current flows through the circuit and passes through the S1 switch because of S2 is open. So that's why S1 the current flows through the S1 and bulb glows. So whenever the current passes through the S1, so that's why we can write that S. The next one, when both S1 and S2 both switches are closed. Both switches are closed, total circuit is connected. So that's why that is whenever the inputs are given that, then S1 and S2 both will be connected. So current flows through the both circuits. These two switches are parallel. These two switches are parallel. So that's why here the current flows and bulb will glows. The resultant Y is equal to A plus B means output we can get that yes. Means here when the A OR operator, in the OP operator, either any switch is connected or any switch is closed or the all switches are closed, then only the output we can get the bulb will glows. When the two switches are open, only the bulb does not glows. So here it is that when S1 and S2 are both are open, then only there is no connection. There is only whenever the two switches are open, there is no current flows through the circuit, bulb does not glows. This is about OR operator. By using this circuit diagram, then OR gate, how the OR gate can be constructed and how the OR gate can be connected in a electrical circuit, how do we get the values, output and input values by connecting the, what is the practically, how can we connect the OR gate in the circuit. Let's see, this is about OR operator. Now we are going to know about the OR gate. So OR gate is having that two or more inputs and one output signal. So there are two or more signals in OR gate and one is output signal. Here is the symbol of the OR gate. Let's see, this can be like a curved. Whenever we are writing the symbol, just listen carefully, see carefully. This can be curved. This is the A terminal. We are giving the inputs here. This is inputs and this is the output we can get that. So the OR gate is having that two or more input signals and one is a output signal. So from that here we can get the truth table like this. Then let's see the realization of OR gate. How do the practical values we can get by using the OR gate. This is we are having the two diodes, that is D1 and D2 diodes, and here is the input. We can get that, we can apply, and we get that output from this place. This is the from the load resistance whatever here, from this place we can get the output values. Let's see how the truth table can be satisfied. How do we get the values? For example, here I am connecting the battery. Consider it's a 5 volts we are applying, and it is grounded at 0 volts. The ground, whenever they are grounded, that is 0 volts. So first of all, the inputs we are giving, that the both are grounded. Both are grounded means A and B are grounded. Whenever both are grounded, then the two diodes are reverse biased. Reverse bias, because of this the plus terminal is minus terminal. Whenever it is grounded, the plus to the minus, and so that's why it will becomes the reverse biased. So whenever it is reverse biased, that A is equal to 0 and B is equal to 0, there is no any conduction between through the diodes. So that's why the output becomes Y is equal to 0. Means input is 0 and output is 0. Whenever the both input terminals are grounded, for example, I just told you that whenever we are applying it is grounded, then here the A is equal to 0, B is equal to 0, because of there is no any conduction through the A and B. Here there is no any conduction through the diode 1 and diode 2, because of they are reversely biased whenever they are both the inputs are connected to the ground. So there is no any output, so that's why Y is equal to 0. That means to say A is equal to 0, B is equal to 0, then Y is equal to 0, because two inputs are grounded. For example, B is grounded. B is grounded means whenever it is grounded, B is equal to 0. The A is connected to the battery, which is having the 5 volts, which is applying the 5 volts battery. One battery is applying the 5 volts. So that's why we are connecting to the A. 5 volts battery we are connecting. Whenever the A is connected in the circuit, that considered as A is equal to 1. A is 1 means it's a closed thing, means it is applied. So the circuit is applied. So 5 volts of current we are giving that. Then the A is B is grounded. So that's why here A is equal to 1 and B is equal to 0. B is equal to 0 means it is reversely biased. D2 is reversely biased. Whenever the battery connected to the D1, it is forwardly biased. Current flows through the D1 diode and voltage we get output. That is whenever the 5 volts voltage is connected to the A input and base is 0, then diode 1 is forwardly biased and diode 2 is reversely biased. So from through the diode D1 the current will flow, then we can get the output voltage from here. That's why Y is equal to 1. Output voltage we can get. Output voltage we can get Y is equal to the resultant according to the Boolean algebra, that is Y is equal to 1. The next one, if in case of A is grounded and B is connected to the battery. A is grounded and B is connected to the battery. A is grounded and B is connected to the battery. When here A is grounded means A is equal to 0 and B is grounded, B is connected means when D1 is reverse biased, whenever it is grounded it is reverse biased, there is no any conduction. So that it's a non-conducting diode, there is no any conduction through the D1, and whenever it is connected to the D2 diode, through the D2 diode the current will flow through that, we can get the output voltage from this output. Whenever we can get the B, D2 diode can allows to pass the current through it, and so that's why we applied the battery 5 volts of battery. Then we can get that B is equal to 1, then Y is equal to 1. Then after that both the terminals are connected to the battery. Both the terminals are connected to the battery. Then D1 and D2 both will be forwardly biased and these two are parallel to each other. Means that is A is equal to 1, conduction will happen through this one, or D1 also conduction will be there, and through the second terminal, that is B input, also there is a conduction, both will be parallel to each other, so that's why output we can get. Like this, when A terminal, A and B terminal both are grounded, means 0, then we can get the output is 0, then only. In this case of, if the inputs, the output signal is high, let's see, the output signal is high if any or all the inputs are high. Let's see, the output signal is high, here is that, the output signal is high if any, here is the one of the I is there, here is the one of the I is there, or both are the high is there. If any or all the inputs are high, if in case of any one input is high in the OR gate, then we can get the output. If the all inputs are high, then also we can get the output. For the OR gate, whatever the logic gate and what are the functioning of OR gate, how do the OR gate is operated in the circuit. Now we are going to know the another gate, another operator of logic gates is a AND operator. This AND operator is used for the multiplication gates, means in Boolean algebra AND operator is used for multiplication, and the sign which is denoted is a dot, means if in case of A and B are the two inputs are which is given to that, A dot B which is equal to Y, this can be the Boolean algebra expression, so that it can be read as A and B is equal to Y, A and B is equal to Y. This is the AND operator. It consists of two inputs, and whenever it is gate is connected in the circuit, it consists of two or more inputs, and one is the output as well as same as OR gate. Here the electrical circuit which is operating, here, that the two switches are in a parallel series, connected in series. In the OR gate, the two switches are in the parallel. So in this case of the two switches are in the series connection, when the switch key is on, S1 and S2 are the inputs, and is the output will be the bulb. Whenever it glows, this will be the output, this is the bulb. When switch 1 is open and switch 2 is also open, so that whenever the battery is connected, there is no any connection between the two switches and to the bulb, so that's why their bulb does not glow. So that's why the bulb glows is no, means S1 is open and S2 is open, bulb does not glow, so that's why we can consider that a no. Then if the bulb glows, no, whenever the two switches are in open. Then either in two switches, if the one switch is closed, means either S2 is closed and S1 is open, the two switches are in series connection. So that's why if the connection S1 is open, that is does not move towards the another end to the another switch S1. So that's why there is no any connection to the S1, which is seriously, S2 is also seriously connected. Even though if the S2 is closed, there is no any conduction current flows through the circuit, then bulb does not glow. This is also no, because of S2. Even though if the S2 is closed, there is seriously connected to the S1, so that's why here S1 is open and S2 is closed, so that's why there is no any conduction to the circuit, so that's why bulb does not glow. And next one, if the S1 is closed, means S1 is closed and S2 is open, even though S1 is closed, the current passes through the circuit and travel through the S1 switch and ends at this place, because of it is opened. Whenever it is opened, there is no any conduction to this end to the other end, so that's why it will be in there is no flows current in the circuit, so that's why bulb output voltage does not we can get, so that's why bulb does not close. So that's why even though if the S1 is closed, S2 is open, so that's why both are in series connection, so that's why if the S1 is closed and S2 is open, there is no bulb glows. The final one, whenever the S1 and S2 both are closed, when the battery is connected, then through the S1 and S2 current flows and through the, so that's why bulb will glow. So that's a yes, means bulb glows. So that's why here we can say that in the AND operator, when the two inputs are high, the output will be high. Means the output will be high when the two inputs are when the two inputs are high, then we can say that the output will be high. If the any one of the terminal is low, there is no any output we can get in the AND gate. So that's why you can say that whenever the two switches are closed, then only we can get the output yes, bulb glows. Otherwise, if any one of the terminal is opened, then their bulb does not glow. So that's why we can't get the output. So from the boolean, in boolean we can say that if 0 0 means the both switches are is open. So that's why here we can't get the output, and here is also the any one of the input is open also we can't get the output. If the two inputs are closed, means two inputs are high, then only we can get the high. So that's why we can get that when the output is high, when the two inputs are high. So that in case of AND gate means it is having the two inputs, two or more inputs and one output is there. So here that there are two or more inputs and one output signal. The output signal high only when the input signals are high. The two input signals who are more, whatever how many the inputs are there, whenever the total inputs are high, then only output we can get the high. In the case of, this is the symbol of AND gate. This is the symbol of, it has to be straight line. In case of OR gate, which is having curved surface. So here observe carefully, this is about AND gate, symbol of AND gate, y is equal to A dot B. So here how the AND gate can be constructed in practically, means by using the diodes. Here D1 and D2 are the diodes which is connected in opposite direction. Let's say we are giving the input to the N type of a terminal, to the N side of a terminal. Whenever it is gives, let's see here, when A and B both are grounded, means both values are 0. So then we can get that output will be 0, as well as we know that whenever grounded it is positively biased, it is conducted, but it is conducted only single charge. So that's why there is no any output voltage can be, it is even though current is conducted, the output voltage will be 0. So that's why we can get that A is equal to 0 and B is equal to 0, output will be 0. If A is grounded and B is connected to the battery, whenever it is reversely biased and it is forwardly biased also, then here whenever it is connected, both will be in reverse bias. So that's why here is also, even though B is connected to the battery, that is also there is no any conduction. So that's why output will be 0. If the A is connected to the battery, B is grounded, then also this will be also there is no any conduction, there is no current flows through the circuit. Even though if it is also grounded 0, it can be connected, but that is in reverse bias. So that is why there is no any conducting there. So that's why this is also output will be 0. If the two are connected to the battery, then due to the minority charge carriers and due to the construction, then we can get that 2 will be in the conduction is there. Whenever the two diodes are parallel, then the output will be there. We can get the output from whenever the two inputs are high, the two inputs are connected to the battery, then only we can get the output is high. In this case, in AND gate, when the two inputs are high, then only the output will be high. This is about AND gate. The next one is according to the truth table, if the A and B are total grounded, then there is no any voltage applied to the output, we can't get the output. And if the A is grounded and B is connected to the battery also, due to the 0 it will be the grounded, and B whenever we connected to the battery, then it is reverse bias. So that's why there is no any conduction, and is also same, then we can't get the output. And whenever the two are connected to the battery, then only we can get the output. Whenever the two we can get the output, means in the cutoff region the voltage will be high. So here is about the AND gate and AND operator. Now we are going to know this. The another one is NOT operator. This is called a NOT operator. It is having that is used for the inversion, means opposite value. Whenever we get the input is high, then output we can get low. So it is also called as a inverter. It is also called as an inverter. This NOT gate is also called as an inverter. So that for the inversion of A, we can write that A is equal to Y is equal to A bar, means bar over whatever the input we are giving, that the bar is a symbol for the NOT operator. So here the circuit design is there. Whenever we get that, whenever the switch is on, the bulb does not glow, means if the switch is open, the straightly conduction to the bulb is there. Switch is open, then straightly battery is connected to the, so that's why bulb will be glows. So that's why S. If the switch is on, then it is parallel to this one. Switch is parallel to bulb. So that's why here there is no any conduction through this one. So that's why whenever it is closed, there is no any bulb glow. So that's why it's no. Means if the input is high, then output is low. If the input is low, then output high, we can get that. Means according to this, the NOT gate can be constructed, it is having the one input and one output. One input and one output. So that's why the output signal is high when input signal is low. Output signal is high when input signal is low. So this is about the symbol of NOT gate. Symbol of NOT gate. By constructing the symbol of NOT gate, if we give the A is high, means A is low, 0, then we can get the Y is equal to opposite to 1. And if we get the A is equal to 1, we can get the, we can give the opposite result. For this, let's see the circuit diagram. For that, how do practically how the NOT gate can be constructed in a realization of NOT gate. Let's see what is the realization of NOT gate. So this is about a realization of NOT gate. Let's see how the practically we connect the NOT gate in the circuit. This is the transistor. This is common emitter transistor, we can use as a NOT gate. In this case of here we can get the input. This is base, collector, emitter. It is the common emitter transistor, we are taking that use as a NOT gate. So from this case, here whenever the input is high, input voltage is high, the transistor driven into the saturation state. The transistor driven into the saturation state, so that the output V out will be less 0. If the V input is high, then transistor moves into the driven into the saturation state, that output voltage becomes a 0. Output voltage becomes a 0. So that when the V input is a low, that means to say if the V input is high, means 1, then transistor moves into the saturation state. So that's why we can get the collector current will be maximum, then the voltage V out, means voltage, output voltage will be decreases. So that's why V out becomes a 0. So that's why there is no any output we can't get. If the V input, the input is low, then the transistor driven into the cutoff state, cutoff region. Whenever the cutoff region, there is no any base voltage in the circuit. So that's why we can get that output voltage we can get the more. So that's why output voltage will be maximum, so that we can get that output voltage. So here is that when the NOT gate is constructed by using the common emitter transistor, if the V input is high, then transistor moves into the saturation state, V out will be 0, means the opposite value we can get. If the V input is high, then we can get the V out will be low. And if the V input is low, then transistor comes to cutoff state, because the base voltage will be less, decreases, then we can get the V output voltage will be high. So that this NOT gate is also called as an inverter. This is used for the inversion. Then Y is equal to A bar will be the, whenever the input inversion for the input value we can get in the NOT gate. This is about AND and NOT gates and the relation of NOT gates. How the construction, how do we construct the NOT gates in the practical purpose also. Now next we are going to discuss about a combination of logic. The logic gates that OR and NOT gates and its operation, how do we connect in the circuit, and what about the function of OR gate according to the truth table we analyzed that, AND gate and NOT gate also. So here the next topic is a combination of logic gates. What is meant by the combination of logic gates? Here two are all the three of gates combined, means connected, then the new logic gate is formed. The new logic gates is the combination of any two or all the three gates. That new gate is there, another gate can be formed. So those are that by combining any two or all the three gates and or NOT gates we can get a new logic gate. Those are, first of all we are going to know this about a NAND gate. NAND gate. Here the NAND gate means, we know that NAND gate is AND gate. We know the AND gate. The output of the AND gate, the output of the AND gate is connected to the input of the NOT gate. Input of the NOT gate means this is the AND gate. Whenever the output of the AND gate becomes the input for the NOT gate, then the new gate is formed called NAND gate. NAND gate, which is according to the value, the output we can get in the NAND gate, which is the inverse values of the AND gate. Once again, the AND gate output becomes the input for the NOT gate is called a NAND gate. This is the NAND gate, this is the symbol of NAND gate. Here y is equal to input is equal to a dot b inverse. Inverse means which is inversion value, which is having that opposite value. If the input is high, then output we can get low. So here is that according to that equation, already we know the AB means the truth table of AND gate, and plus NOT gate is equal to NAND gate we can get. NAND gate we can get. So here this is the AND gate and this is the NOT gate. From these two gates we got that NAND gate. This is a NAND gate. According to the truth table is, whenever the two inputs are high, only the output will becomes high in the AND gate. We know that when all the inputs are high, only the output will be. When the inputs are total, all the inputs are high only, then only the output will be high. In case of another thing, the output will be low. Here that A and B are the inputs. Let's see, AB means the values of AB are grounded, means either we are giving the low values, then we can get the low, and one of the low value and one is another one is B is high, then we can get the output is low in AND gate. And the input A is high and B is low, then we can get the output is low in a AND gate. In a AND gate, whenever the two inputs are high, then only we can get the output is high in AND gate. We know that this is about AND gate. The NAND gate means which is the inverse values of the AND gate. Here when the two inputs are low, then we can get the NOT gate and NAND gate is the output will be high. If in case of a NAND gate, when the two inputs are high, then output will be low in case of NAND gate, like this. If any or the both or all the inputs are low, if any or all the inputs are low, then output will be high in a NAND gate. Here is that if any input is given that 0 0 is low, then we can get the output is high. Then here A is low and B is high, then output will be high. And here whenever the value A is high and B is low, then we got the value A, the NAND gate, according to the NAND gate high. When the two inputs are high in the NAND gate, then output will be low. And also the NAND gate is also called as a universal gate. This NAND gate is also called as a universal gate. Because of, by using the NAND gate, we can construct the another gates. We can construct the OR and NOT gates also by connecting the, whenever the inputs of, this is the NAND gate, whenever the inputs of NAND gates connected together, whenever the NAND gates inputs connected together, then this NAND gate behaves like a NOT gate. When the inputs of a NAND gate connected together, then we can construct that NOT gate will be formed, means NOT gate will be becomes a NOT gate. So that's why by using the NAND gate, it can form this is called blocks. By using these blocks, then whenever the two inputs of NAND gate combined, then it is a NOT gate is formed. So that's why we can construct the, by using the NAND gate, we can construct the logic gates, general logic gates, or and NOT. So that's why this NAND gate is called as a universal gate. NAND gate is called as a universal gate. When, once again, whenever the two inputs are high in the NAND gate, then only we can get the output value is low. In all other cases, we can get the high value. Means whenever the two inputs or any one of the input is becomes low, then output becomes high in the NAND gate. And NAND gate is also called as a universal gate, because of by using the NAND gate we can construct the, we can construct the another general OR and NOT gates, so we can construct the also. So that's why that universal, the NAND gate is called as a universal gate. And one more thing is, this is the symbol of a NAND gate. Whenever the two inputs of the NAND gate is connected together, then the NOT gate will be formed. It will behave like a NOT gate. So that's why it can get, NOT gate can be constructed by connecting the two inputs of the NAND gate together. This is about a NAND gate. Next come for the NOR gate. This is also one of the universal gate. Universal gate. The NAND gate is also called as another universal gates are called as NAND, and NOR gates are called as universal gates. So in this case of universal gates, NOR gate is also considered as a universal gate. In this case of, when the output of the OR gate is becomes the input for the NOT gate, then NOR gate will be formed. NOR gate will be formed. This is the OR gate and this is a NOT gate. Whenever the OR gate output is becomes input for the NOT gate, then NOR gate is formed. We can get the values which is in OR operation, we got the values for that. We can get the inverse values for that, means opposite values for the OR gate. So here is that when the A and B, here this is the Boolean expression for the NOR gate. Here A, B is the inputs and A plus B is the AND gate and output, and whenever it is connected to the NOT gate, then we can get Y is equal to A plus B bar. The NOT gate is considered as bar. So here the A and B values are low, as well as the value becomes low in OR gate. And each and every one, we know that in the OR gate, any one of the input or all the inputs are high, then the output will becomes high in the OR gate. So in that case, here is a 0 0 means low value is there. We can get the low value. Either if any one of the value is high, means 0 1 becomes 1 1 0 1 1 1 1, means either one of the value is high or two values are high. One or all the inputs are high, only we can get in the OR, that will be the OR gate. If we come for the NOR gate, whenever we connected the NOT gate to the OR gate, then it can be formed here OR plus NOT is equal to NOR gate. NOR gate is formed. So that's why here whenever the inputs are low, then output will becomes high in the case of NOR gate. So whenever the two inputs are low, then only the output will becomes high in the NOR gate. In all other cases, if the two inputs are high or either any one of the input is high, also we can get the low value in the NOR gate. And by using this NOR gate also we can construct the OR and NOT gate. So that's why we can say that here the NAND and NOR gates are called as universal gates, because of by using these two gates we can construct the another gates. So it is called as universal gates. This is about the brief information about the gates. And if we come for if we want to discuss about more gates, then XOR gates is there, XNOR gates is there, and more of the type of gates also there. By using these gates also we can construct those gates. So this is about